Subscribe to the channel so you don't miss out on any of these videos. Imagine this. The universe at its most fundamental level isn't made of objects you can see or touch, but instead is a symphony of tiny, vibrating strings, particles popping in and out of existence, and forces so abstract they defy our intuition. Now, zoom out and think about the universe as a whole, a vast, curved space-time continuum where colossal celestial bodies like stars and black holes warp the fabric of reality itself. These two perspectives, the microscopic quantum world and the macroscopic domain of general relativity, should fit together like pieces of a puzzle. But they don't. At least, not yet. This is the mystery of quantum gravity, the ultimate theory that scientists believe could unify our understanding of the cosmos. Why does this matter? Because without solving it, we can't truly understand black holes, the Big Bang, or the very nature of existence. It's as if the universe is keeping its deepest secrets locked away, teasing us with clues but never giving up the full picture. Quantum mechanics and general relativity are like two different languages spoken by the universe. Quantum mechanics describes the universe at the smallest scales, atoms, particles, and even the strange behavior of energy itself. It's weird, counterintuitive, and sometimes feels like it's playing tricks on our minds. On the other hand, general relativity is a grand, elegant theory that describes the universe at its largest scales. It tells us how massive objects bend space-time, how planets orbit stars, and how black holes form. Both theories work incredibly well in their own domains. But when they meet, say, inside a black hole or at the very beginning of the Big Bang, they completely break down. The math simply stops working. This isn't just a minor inconvenience. It's a catastrophic failure of our understanding. And that's why physicists have been searching for a way to merge these two theories for nearly a century. They're looking for the theory of quantum gravity, a framework that can describe the universe at all scales, from the tiniest particles to the largest galaxies. Let's dive into what this means and why it's so challenging. To do that, we need to start by understanding what makes quantum mechanics and general relativity so different. Quantum mechanics is all about probabilities. Imagine rolling a die, but instead of landing on a single number, it exists as a mixture of all possibilities until you look at it. That's essentially how particles behave at the quantum level. Electrons don't orbit atoms like tiny planets. They exist as clouds of probability. Particles can be in two places at once, and they can even affect each other instantaneously across vast distances, a phenomenon called quantum entanglement. General relativity, however, is deterministic. If you know the position and velocity of an object, you can predict its future trajectory with absolute certainty. It's a theory rooted in the smooth, continuous fabric of space and time. Gravity, according to Einstein, isn't a force pulling objects together. It's the curvature of space-time caused by mass and energy. Imagine placing a bowling ball on a trampoline. The trampoline sags, and smaller objects roll toward the ball. That's how gravity works on a cosmic scale. Here's the problem. When you try to combine the probabilistic nature of quantum mechanics with the smooth, continuous framework of general relativity, you get nonsense. The equations blow up into infinities, producing results that don't make any physical sense. This clash becomes especially apparent in extreme environments like the center of a black hole, where the density of matter becomes infinite, or the moment of the Big Bang, where the universe was infinitely small and dense. One of the biggest challenges in developing a theory of quantum gravity is finding a way to describe space-time itself as a quantum object. In general relativity, space-time is a smooth, continuous fabric. But in quantum mechanics, everything is discrete, made of tiny, indivisible units. How do you reconcile these two ideas? Some physicists propose that space-time might be made of tiny, fundamental units, much like matter is made of atoms. These units would be unimaginably small, far beyond the reach of current technology to detect. String theory is one of the leading contenders for a theory of quantum gravity. Instead of thinking of particles as tiny points, string theory suggests that they're tiny, vibrating strings. The way these strings vibrate determines the properties of the particles they form, such as their mass and charge. What's fascinating about string theory is that it naturally includes gravity, along with all the other fundamental forces of nature. But there's a catch. String theory requires extra dimensions of space. Instead of the 3 dimensions we experience, string theory suggests there are 10 or even 11 dimensions, most of which are curled up so small we can't see them. Another approach is loop quantum gravity, which takes a different perspective. Instead of trying to describe particles as strings, it focuses directly on spacetime itself. Loop quantum gravity suggests that spacetime is made of tiny loops, woven together like a fabric. This theory predicts that space and time are quantized, broken into tiny, discrete chunks. One of the most exciting implications of loop quantum gravity is that it might eliminate the singularities at the center of black holes and the Big Bang. Instead of infinities, we'd have a finite, well-defined structure. But here's where it gets even stranger. Some physicists believe that the key to quantum gravity might lie in completely rethinking our understanding of reality. The holographic principle, for example, suggests that our 3-dimensional universe might actually be a projection of information stored on a 2-dimensional surface. This idea comes from studying black holes, which seem to encode information about everything that falls into them on their 2-dimensional event horizons. If this principle applies to the entire universe, it could mean that space and time themselves are emergent properties, arising from something even more fundamental. Then there's the concept of quantum foam, proposed by physicist John Wheeler. At the smallest scales, space-time might not be smooth and continuous but instead frothy and chaotic, with tiny wormholes and bubbles constantly forming and disappearing. This quantum foam could hold the key to understanding how space-time behaves at the Planck scale, the incredibly tiny scale where quantum gravity effects become significant. The search for quantum gravity isn't just about abstract math and theory. It has real-world implications for some of the biggest mysteries in physics. For example, understanding quantum gravity could reveal what happens inside black holes and whether information that falls into them is truly lost forever. It could explain the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. And it could finally answer the question of what caused the Big Bang, how the universe came into existence from nothing. The stakes in the search for quantum gravity are monumental because it could redefine everything we think we know about the universe. But where do we stand today? Scientists have proposed several tantalizing ideas, yet none have been definitively proven. Let's dig deeper into these theories, their implications, and the challenges that come with them. String theory, for instance, isn't just a mathematical construct, it's a vision of a universe where everything is interconnected. Each string vibrates at its own frequency, creating the particles and forces we observe. In this framework, gravity naturally emerges as one of the vibrations. This idea is beautiful and elegant, but it comes with an enormous downside. It's almost impossible to test. The strings are so small, trillions of times smaller than an atom, that no current or foreseeable technology can directly observe them. Furthermore, the additional dimensions required by string theory are compactified, meaning they are folded up in ways we can't easily detect. Despite its challenges, string theory has made some predictions that intrigue physicists. For example, it suggests the existence of supersymmetry, a theoretical symmetry between particles and their heavier counterparts. If supersymmetry were confirmed, it would provide strong support for string theory. However, experiments at the Large Hadron Collider have yet to find definitive evidence for supersymmetric particles, leaving the theory on shaky ground. Loop quantum gravity, on the other hand, focuses on making predictions about spacetime itself. One of its most exciting propositions is that the Big Bang wasn't the beginning of everything. Instead, it might have been a big bounce, where a previous universe collapsed, and its remnants formed the universe we inhabit today. This idea challenges the conventional view of the Big Bang as the ultimate origin, suggesting instead a cyclical model of creation and destruction. But even loop quantum gravity faces significant hurdles. Its mathematical framework, while promising, is incomplete. And like string theory, it's difficult to test experimentally. The effects of quantum gravity only become significant at the Planck scale, which is far beyond the reach of any current experiment. For now, scientists must rely on indirect evidence, like studying the behavior of black holes or examining the cosmic microwave background for subtle quantum imprints. Speaking of black holes, they're among the best laboratories we have for studying quantum gravity. Black holes are places where the clash between quantum mechanics and general relativity becomes unavoidable. At their cores lies a singularity, a point of infinite density where our current theories break down. This is precisely where a theory of quantum gravity is needed. Stephen Hawking's groundbreaking work on black holes introduced the concept of Hawking radiation, where quantum effects at the event horizon cause black holes to emit particles and slowly evaporate over time. But this raises a profound question: what happens to the information about the objects that fall into a black hole? According to quantum mechanics, information cannot be destroyed, yet general relativity suggests it's lost forever inside the singularity. This paradox, known as the black hole information paradox, remains one of the biggest mysteries in physics. Resolving it will require a complete theory of quantum gravity. The holographic principle offers a fascinating potential solution. It suggests that all the information about the three-dimensional universe could be encoded on a two-dimensional surface, much like a hologram. In the context of black holes, this means that the information about everything that falls in might be stored on the event horizon. Extending this idea to the entire universe could revolutionize our understanding of space, time, and reality itself. The Big Bang is another area where quantum gravity is essential. The moment of the Big Bang marks a singularity, an infinitely small and dense point where the laws of physics as we know them cease to function. General relativity can describe the universe immediately after the Big Bang, but it can't explain what caused it or what came before. Quantum gravity could provide the missing link, revealing how space and time themselves emerged from a quantum state. One speculative idea is that the universe began as a quantum fluctuation, a spontaneous, momentary disturbance in a quantum field. This could explain how something arose from nothing, but it raises deeper questions about the nature of this nothing and the origins of the quantum laws themselves. Another possibility is that the universe has always existed in some form, cycling through phases of expansion and contraction. The implications of quantum gravity extend far beyond black holes and the Big Bang. It could also help us understand dark energy and dark matter, the mysterious components that make up most of the universe. Dark energy is driving the accelerated expansion of the universe, while dark matter provides the unseen gravitational glue that holds galaxies together. Both phenomena remain poorly understood, but quantum gravity might offer clues about their origins and properties. Another intriguing avenue is the study of quantum foam. If space-time is fundamentally discrete, then at the smallest scales, it might resemble a frothy, chaotic sea. This quantum foam could give rise to phenomena like virtual particles, which constantly pop in and out of existence, and even tiny wormholes that connect distant points in space-time. Understanding this foam could unlock the secrets of spacetime's quantum nature. Some researchers are also exploring the possibility that gravity itself might not be a fundamental force but an emergent phenomenon. According to this view, gravity could arise from the collective behavior of more basic quantum entities, much like temperature emerges from the motion of atoms. This radical idea could change how we think about the universe and its fundamental forces. The search for quantum gravity is one of the most ambitious quests in science, and progress is slow but steady. Experimental breakthroughs might come from unexpected places, such as studying gravitational waves, which are ripples in space-time caused by massive cosmic events. These waves could carry subtle imprints of quantum gravity, offering a glimpse into the quantum nature of space-time. In the meantime, the search continues, driven by the hope that we'll one day unlock the ultimate secrets of the universe. Solving the mystery of quantum gravity isn't just about unifying physics. It's about answering the most profound questions about existence itself. Why does the universe exist? What is the nature of reality? And what lies beyond the horizons of our current understanding? One of the most exciting aspects of the quest for quantum gravity is its potential to fundamentally alter our perception of reality. If we manage to reconcile quantum mechanics and general relativity, we might discover that the universe operates on principles we've never imagined. The limitations of our current understanding leave vast open spaces for groundbreaking discoveries, and each new insight brings us closer to answering existential questions. Consider the concept of time. In our everyday experience, time flows like a river, unidirectional and constant. General relativity already challenges this notion, showing that time is relative. It slows down near massive objects or at high speeds. But quantum mechanics hints at an even stranger reality. At the smallest scales, time might not be continuous at all. Instead, it could be quantized, existing in discrete chunks. If quantum gravity reveals that space and time are fundamentally granular, this would overturn millennia of human thought about the nature of existence. Another fascinating implication is the possibility of multiverses. Quantum mechanics already introduces the idea of multiple possibilities coexisting in superposition, only collapsing into a single state upon observation. Some interpretations of quantum gravity suggest that these possibilities could extend to entire universes. In this view, our universe might be just one of countless others, each governed by different physical laws. The very idea challenges our understanding of reality, making us question whether our universe is unique or part of a grander cosmic tapestry. Black holes remain central to these explorations. The event horizon, where gravity becomes so strong that nothing, not even light, can escape, is a boundary between the observable universe and the unknown. Yet quantum effects suggest that the event horizon might not be as impermeable as we think. Some theories propose that the information falling into a black hole isn't lost but instead encoded in subtle quantum states at the event horizon. This ties into the holographic principle, which posits that all the information about a three-dimensional volume can be stored on its two-dimensional boundary. Expanding this idea, the entire universe could be a hologram, a three-dimensional projection of information encoded on a two-dimensional surface. This isn't just a poetic metaphor. It's a mathematical framework that some physicists are actively exploring. If true, it would mean that our experience of reality is, in a sense, an illusion, a shadow of deeper, underlying truths. The study of quantum gravity also forces us to confront the ultimate nature of space. We think of space as a vast, empty arena where events unfold, but quantum mechanics suggests it's far more dynamic. At the smallest scales, space might be a seething foam of virtual particles, constantly flickering in and out of existence. This quantum foam could provide the scaffolding for the universe, influencing the behavior of particles and forces in ways we're only beginning to understand. One of the most ambitious ideas in quantum gravity is the concept of emergent space-time. In this view, space and time aren't fundamental entities but emergent properties arising from more basic quantum processes. Imagine a computer simulation. The digital code is the fundamental reality, while the simulated world is an emergent phenomenon. Similarly, space-time might emerge from deeper quantum laws we have yet to uncover. These theories are not just academic exercises. They have profound implications for understanding the origins of the universe. The Big Bang singularity is a glaring problem in our current models because it represents a point where the equations of general relativity break down. Quantum gravity could provide a more complete picture, showing how the universe transitioned from a quantum state to the classical cosmos we observe today. One hypothesis is that the Big Bang wasn't a singular beginning but a quantum event, a fluctuation in a pre-existing quantum field. In this scenario, the universe could have emerged from nothing. Not as a void but as a state devoid of classical definitions of space and time. This idea ties into the concept of vacuum energy, a pervasive field that could spontaneously generate particles and even entire universes. Another possibility is the bounce model, where a previous universe contracted under its own gravity, eventually reaching a state of extreme density. Instead of collapsing into a singularity, quantum effects caused it to rebound, creating the expanding universe we see today. This cyclical model challenges the conventional view of the Big Bang as the ultimate beginning, suggesting instead an eternal sequence of universes. The implications of these ideas extend to the ultimate fate of the universe. If the universe is cyclic, it might eventually stop expanding, collapse, and give rise to a new Big Bang. Alternatively, if dark energy continues driving the accelerated expansion, the universe could end in a big freeze, where all matter is so spread out that no interactions are possible. Quantum gravity could help us understand these scenarios by revealing the underlying laws that govern cosmic evolution. Quantum gravity also has practical implications for understanding the most extreme environments in the universe. Neutron stars, for instance, are incredibly dense remnants of massive stars. In their cores, matter is compressed to densities where quantum and relativistic effects become inseparable. Studying these objects could provide clues about how quantum gravity operates in such extreme conditions. Similarly, the study of gravitational waves offers a new window into the universe. These ripples in spacetime, first predicted by Einstein and confirmed in 2015, could carry information about quantum gravitational effects. For instance, if black holes merge in a way that creates anomalies in the expected gravitational wave patterns, it might point to new physics beyond our current understanding. As we push the boundaries of knowledge, we're also developing new tools and technologies to test these ideas. High-energy particle accelerators, like the Large Hadron Collider, probe the fundamental forces of nature at unprecedented scales. Meanwhile, advances in quantum computing and experimental physics are opening new avenues for exploring the quantum nature of reality. The search for quantum gravity isn't just a scientific quest, it's a philosophical one. It forces us to question the very nature of existence, reality, and our place in the cosmos. Are we merely observers of a grand, deterministic machine, or do we play an active role in shaping the universe through our observations? Quantum mechanics already suggests that observation plays a role in determining reality, but how this principle scales up to the cosmos remains an open question. As we continue to unravel the mysteries of quantum gravity, one thing is clear: the journey is just as important as the destination. Each step brings us closer to understanding not only the universe but also ourselves, our origins, our future, and the profound interconnectedness of all things. The quest to understand quantum gravity has also ignited debates about the very fabric of the universe. One of the most contentious and intriguing ideas is that reality may be fundamentally non-local. Non-locality, a cornerstone of quantum mechanics, suggests that particles can instantaneously influence each other, regardless of the distance separating them. This phenomenon, known as quantum entanglement, defies our classical understanding of causality and spacetime. If quantum gravity incorporates non-locality, it could mean that the universe operates on principles far beyond our intuitive grasp. For example, entangled particles seem to share information instantaneously, even across vast distances. This spooky action at a distance, as Einstein famously described it, has been experimentally confirmed multiple times. But how does this fit into a universe governed by general relativity, where nothing can travel faster than the speed of light? The reconciliation of these ideas might require rethinking spacetime itself. Some physicists suggest that entanglement could be the fundamental building block of spacetime, stitching together the fabric of the universe. This perspective ties into the concept of quantum foam, where spacetime at the Planck scale, a minuscule scale of about meters, is thought to be wildly turbulent. In this foam, the smooth continuum of spacetime breaks down, replaced by a chaotic, probabilistic structure. Quantum gravity aims to describe this foam mathematically and understand how it gives rise to the stable, predictable universe we observe on larger scales. The role of black holes in quantum gravity continues to captivate scientists. Black holes are essentially laboratories for testing the interplay between quantum mechanics and general relativity. The paradox of information loss in black holes has spurred some of the most groundbreaking theoretical work in the field. According to classical general relativity, anything that falls into a black hole is lost forever, its information erased. However, quantum mechanics insists that information must be preserved. This clash has led to proposals like Hawking radiation, which suggests that black holes slowly emit radiation and could eventually evaporate, releasing their stored information in some form. The implications of this are profound. If black holes do preserve information, it could validate the holographic principle. This principle, inspired by studies of black hole thermodynamics, suggests that all the information within a volume of space can be encoded on its boundary. If true, this principle might apply not just to black holes but to the entire universe, fundamentally altering our understanding of dimensions and reality. Further expanding on this idea is the concept of spacetime dualities, such as the ADS/CFT correspondence. This mathematical framework proposes that a gravitational theory in a higher dimensional space, like an anti-de Sitter space, is equivalent to a quantum field theory on its lower dimensional boundary. In simpler terms, the physics inside a space can be described entirely by the physics on its surface. This duality provides a powerful tool for studying quantum gravity, offering insights into both black holes and cosmology. When it comes to cosmology, quantum gravity could illuminate the earliest moments of the universe. The Big Bang represents a singularity, a point of infinite density and temperature where general relativity breaks down. Quantum gravity seeks to replace this singularity with a more comprehensive description, potentially revealing how the universe emerged from a quantum state. One possibility is that the universe began as a quantum fluctuation, arising from the vacuum energy of space itself. This leads to another fascinating idea, the multiverse. If quantum fluctuations can create universes, then ours might be one of many, each with its own physical laws. Some of these universes might be completely unrecognizable, with different constants, dimensions, or forms of matter. The multiverse hypothesis raises profound philosophical questions about our place in existence, and whether the conditions of our universe are uniquely suited for life, or simply a product of chance. The study of quantum gravity also intersects with other cutting-edge areas of physics, such as string theory and loop quantum gravity. String theory, for instance, replaces point-like particles with one-dimensional strings vibrating at different frequencies. These strings exist in higher dimensions, which are compactified and hidden from our perception. String theory naturally incorporates gravity, offering a potential framework for quantum gravity. However, its predictions are challenging to test experimentally, leading to debates about its scientific validity. Loop quantum gravity, on the other hand, focuses on quantizing spacetime itself. It suggests that spacetime is composed of discrete loops, or networks, forming a granular structure. This approach avoids some of the complexities of string theory and makes concrete predictions, such as the existence of a minimum length scale. While both theories have their strengths and weaknesses, they represent complementary efforts to understand quantum gravity. The search for quantum gravity has also inspired entirely new branches of mathematics and computational science. Concepts like noncommutative geometry and twistor theory have emerged as potential tools for describing the quantum structure of spacetime. Meanwhile, advancements in quantum computing offer hope for simulating complex quantum systems that are currently beyond our reach. As we push deeper into this uncharted territory, one thing becomes clear: the journey toward quantum gravity is as much about expanding our intellectual horizons as it is about solving equations. Each new discovery challenges our assumptions and forces us to confront the limits of human knowledge. Whether we're peering into the heart of a black hole, exploring the origins of the universe, or contemplating the nature of reality itself, the quest for quantum gravity reminds us of the boundless potential of science to illuminate the mysteries of existence. In many ways, the pursuit of quantum gravity mirrors the broader human quest for understanding. It's a journey that requires imagination, collaboration, and an unyielding curiosity about the universe we inhabit. And while the road ahead is uncertain, the possibilities are endless, promising revelations that could redefine our place in the cosmos. The search for quantum gravity isn't merely a scientific challenge, it's a philosophical odyssey. It forces us to question the very foundations of reality, compelling us to ask, what is the universe made of? How does it work at its most fundamental level? And perhaps most intriguingly, why does it exist at all? These questions have haunted humanity for centuries, and quantum gravity stands as a modern battleground for tackling them. One of the most profound implications of quantum gravity is its potential to unify our understanding of the smallest and largest scales of the universe. On the smallest scales, quantum mechanics reigns supreme, describing particles, fields, and their interactions with astonishing precision. On the largest scales, general relativity offers an elegant description of spacetime, gravity, and the dynamics of celestial bodies. However, these two frameworks are fundamentally incompatible, and bridging this gap is the ultimate goal of quantum gravity. Take, for example, the concept of spacetime itself. In general relativity, spacetime is a smooth, continuous fabric that can be warped by the presence of mass and energy. But in the realm of quantum mechanics, nothing is continuous. Everything is quantized, divided into discrete, indivisible units. This contradiction suggests that spacetime might not be as smooth as it appears. Instead, it could be made up of tiny, discrete elements, much like the individual pixels in a digital image. Quantum gravity seeks to uncover these spacetime pixels and understand how they collectively give rise to the smooth universe we experience. This granular nature of spacetime could have far-reaching implications. For instance, it might explain why we perceive time as flowing in one direction. At macroscopic scales, time appears continuous and irreversible, governed by the second law of thermodynamics. But at the quantum level, the distinction between past and future becomes blurred. Understanding how time emerges from the quantum structure of spacetime could revolutionize our perception of reality and solve one of physics' deepest mysteries. Another area where quantum gravity could shed light is the nature of black holes. These enigmatic objects are the ultimate testbeds for exploring the interplay between quantum mechanics and general relativity. At their cores lies a singularity, where densities become infinite, and our current theories break down. However, quantum gravity might eliminate singularities altogether, replacing them with finite, comprehensible structures. Some theories propose that the cores of black holes could harbor exotic quantum states of matter, while others suggest they could be gateways to other regions of the universe, or even other universes. The study of black holes also intersects with the notion of information. In classical physics, information about a system is never lost. But in the context of black holes, information seems to disappear when matter crosses the event horizon. This apparent contradiction has sparked debates for decades, culminating in the famous black hole information paradox. Quantum gravity might resolve this paradox, demonstrating how information is preserved even in the presence of extreme gravitational fields. This resolution could have profound implications for our understanding of entropy, thermodynamics, and the fundamental laws of physics. Another fascinating aspect of quantum gravity is its potential to explain the Big Bang. The Big Bang represents a singularity, a point where densities and temperatures become infinite, and our current understanding collapses. Quantum gravity could provide a more accurate description of this moment, revealing what happened at, or even before, the Big Bang. Some theories suggest that the Big Bang was not a singularity but a bounce, where a prior contracting universe rebounded into the expanding one we observe today. This idea, known as the Big Bounce, aligns with certain quantum gravity models and challenges the traditional view of the universe's origin. The exploration of quantum gravity has also led to new interpretations of the cosmos. For instance, some theories suggest that our universe is a hologram, with all the information about its contents encoded on a two-dimensional surface. This holographic principle, inspired by studies of black hole thermodynamics, offers a radically different perspective on space and time. If true, it could mean that the three-dimensional reality we experience is an emergent phenomenon, much like a 3D image projected from a 2D film. Additionally, quantum gravity might help us understand the dark components of the universe, dark matter and dark energy. Dark matter, which makes up about 27% of the universe, interacts with ordinary matter through gravity but remains invisible to direct detection. Dark energy, accounting for 68% of the universe, drives the accelerated expansion of space. Both phenomena defy explanation within the frameworks of quantum mechanics and general relativity. Quantum gravity could provide new insights into these mysterious entities, potentially unveiling entirely new forms of matter and energy. Another exciting frontier is the potential experimental confirmation of quantum gravity. While directly probing Planck-scale phenomena is currently beyond our technological capabilities, researchers are developing ingenious methods to test quantum gravity indirectly. For example, certain theories predict deviations from classical physics in the behavior of particles at extremely high energies or in the patterns of cosmic microwave background radiation. Detecting such deviations could provide crucial evidence for the validity of quantum gravity models. Meanwhile, advancements in quantum computing and artificial intelligence are opening up new avenues for exploring quantum gravity. These technologies allow scientists to simulate complex quantum systems, test theoretical predictions, and analyze massive datasets with unprecedented precision. As computational power continues to grow, the dream of experimentally probing the quantum structure of spacetime may become a reality. Ultimately, the quest for quantum gravity is more than just a scientific endeavor. It's a testament to humanity's insatiable curiosity and drive to understand the cosmos. Each step forward brings us closer to answering age-old questions about the nature of existence, the origins of the universe, and our place within it. And while the journey is fraught with challenges, the potential rewards are immeasurable, promising to transform not only our understanding of the universe but also our perspective on ourselves and our place in the grand cosmic tapestry. The implications of quantum gravity extend beyond theoretical physics, touching on profound philosophical and existential questions. If spacetime is not fundamental but emergent, as some theories suggest, what does that say about our understanding of reality? Are space and time merely convenient constructs of the human mind, or do they possess an objective existence independent of observation? These questions blur the line between physics and metaphysics, pushing the boundaries of what we consider knowable. One of the most fascinating aspects of this debate is the idea that reality might not be local. Locality, a cornerstone of classical physics, assumes that objects are only influenced by their immediate surroundings. However, quantum mechanics shatters this notion with phenomena like entanglement, where particles separated by vast distances can instantaneously affect each other. If non-locality is an intrinsic feature of the universe, it could mean that spacetime itself is an emergent property of deeper, non-local principles. This idea gains traction in approaches like loop quantum gravity and string theory. Loop quantum gravity proposes that spacetime is composed of tiny, discrete loops or networks, which can give rise to the illusion of continuity. String theory, on the other hand, posits that the universe's fundamental building blocks are not particles but one-dimensional strings vibrating at different frequencies. These strings exist in higher dimensional spaces, some of which are compactified and hidden from our perception. Both theories challenge our classical understanding of space and time, suggesting that our everyday experience is just the tip of the iceberg. The interplay between quantum mechanics and general relativity also raises questions about the nature of causality. In classical physics, cause and effect are straightforward. Events in the present are determined by events in the past. But in the quantum realm, causality becomes probabilistic. Particles don't follow deterministic paths. Instead, their behavior is governed by probabilities. This probabilistic nature becomes even more complex when combined with the curvature of spacetime predicted by general relativity. Quantum gravity seeks to reconcile these perspectives, potentially redefining what we mean by causality itself. The potential applications of quantum gravity extend to some of the most perplexing mysteries in cosmology. Dark matter and dark energy, which together make up 95% of the universe, remain enigmatic. Dark matter interacts with ordinary matter through gravity but is invisible to electromagnetic radiation, making it detectable only through its gravitational effects. Dark energy, on the other hand, is responsible for the accelerated expansion of the universe. Both phenomena defy explanation within the frameworks of quantum mechanics and general relativity, suggesting that quantum gravity might hold the key to understanding them. Some theories propose that dark matter could consist of exotic quantum particles, such as WIMPs, weakly interacting massive particles, or axions. Quantum gravity might provide insights into the behavior and interactions of these particles, offering clues about their nature. Similarly, dark energy could be linked to the quantum structure of spacetime itself. For instance, it might arise from the energy of the quantum vacuum, a concept that quantum gravity could help refine and quantify. The study of quantum gravity also intersects with the origins of the universe. The Big Bang represents a singularity where densities and temperatures become infinite, and our current theories break down. Quantum gravity could replace this singularity with a more comprehensive model, revealing what happened at or before the Big Bang. Some approaches suggest that the universe might have undergone a bounce, where a prior contracting phase transitioned into the expanding phase we observe today. This idea challenges the traditional view of the universe's origin and opens up new possibilities for understanding its evolution. Additionally, quantum gravity could provide insights into the arrow of time, the observation that time flows in one direction, from past to future. At macroscopic scales, this arrow is governed by the second law of thermodynamics, which states that entropy, or disorder, tends to increase over time. But at the quantum level, time appears reversible, with no intrinsic direction. Quantum gravity might bridge this gap, explaining how the irreversible flow of time emerges from the quantum structure of space-time. Experimental efforts to probe quantum gravity are gaining momentum, despite the immense challenges involved. Directly testing phenomena at the Planck scale is currently beyond our technological capabilities, as this scale is far smaller than what our most advanced instruments can resolve. However, indirect methods are being developed to test the predictions of quantum gravity. For example, deviations from classical physics might be detectable in the behavior of particles at extremely high energies or in the polarization patterns of the cosmic microwave background radiation. Observing such deviations could provide crucial evidence for quantum gravity theories. Quantum gravity also has implications for the study of black holes, which are natural laboratories for testing the interplay between quantum mechanics and general relativity. The information paradox, which arises from the apparent loss of information in black holes, challenges our understanding of fundamental physics. If information is truly lost, it violates the principles of quantum mechanics. Quantum gravity could resolve this paradox by showing how information is preserved, even in the extreme environments of black holes. One intriguing possibility is that black holes might not be as black as they seem. Theoretical work by Stephen Hawking suggests that black holes emit radiation, known as Hawking radiation, due to quantum effects near the event horizon. This radiation could allow black holes to slowly evaporate over time, potentially releasing the information they contain. Understanding this process requires a comprehensive theory of quantum gravity, as it involves both quantum mechanics and general relativity. The holographic principle offers another perspective on black holes and quantum gravity. Inspired by studies of black hole thermodynamics, this principle suggests that all the information within a volume of space can be encoded on its boundary. If true, the holographic principle could apply not just to black holes but to the entire universe, fundamentally altering our understanding of dimensions and reality. This idea ties into the ADS/CFT correspondence, a mathematical framework that equates a gravitational theory in a higher dimensional space with a quantum field theory on its lower dimensional boundary. The implications of these ideas extend to the multiverse hypothesis, the notion that our universe is just one of many. If quantum fluctuations can give rise to entire universes, then the multiverse might be a natural consequence of quantum gravity. Each universe could have its own physical laws, constants, and dimensions, offering a vast and diverse cosmic landscape. While the multiverse remains a speculative concept, it challenges our understanding of uniqueness and raises profound philosophical questions about the nature of existence. In this context, quantum gravity serves as a bridge between the known and the unknown, providing a framework for exploring the deepest mysteries of the cosmos. As we continue to unravel its complexities, we gain not only a better understanding of the universe but also a deeper appreciation for the interconnectedness of all things. The journey toward quantum gravity is a testament to human ingenuity, curiosity, and the enduring quest for knowledge. The concept of quantum gravity has also inspired discussions about the fundamental nature of reality itself. If space-time is emergent rather than fundamental, as some theories suggest, then what we perceive as reality might be just a projection or a construct derived from deeper principles. This idea is both fascinating and unsettling, as it challenges our most basic assumptions about existence. One prominent interpretation within this framework is the notion that reality might be digital rather than analog. In this view, the universe could be seen as a kind of computational system, with space-time consisting of discrete units, much like the pixels on a screen. Theoretical physicist John Archibald Wheeler famously summarized this idea with the phrase, it from bit, suggesting that all physical entities are ultimately manifestations of informational processes. Quantum gravity, with its focus on the smallest scales of the universe, provides fertile ground for exploring this hypothesis. This digital perspective is supported by the quantization of spacetime in theories like loop quantum gravity. In this framework, spacetime is composed of finite, indivisible units called quantum loops, which form a dynamic network. These loops are not static but evolve over time, giving rise to the fabric of spacetime as we experience it. The idea that spacetime is quantized aligns with the broader principle of quantum mechanics, where energy and other physical properties are also quantized. Another intriguing implication of quantum gravity is the potential to unify disparate concepts in physics. For instance, the duality between particles and waves in quantum mechanics might find a deeper explanation within a quantum gravity framework. Similarly, the equivalence of mass and energy, as described by Einstein's famous equation, could be reinterpreted in terms of the geometry of spacetime at the quantum level. These unifications would not only simplify our understanding of the universe but also open up new avenues for technological innovation. Quantum gravity also sheds light on the nature of vacuum energy, a concept central to both quantum mechanics and cosmology. The vacuum is not truly empty but teems with virtual particles that pop in and out of existence. This quantum foam has measurable effects, such as the Casimir effect, where two closely spaced metal plates experience an attractive force due to changes in the vacuum energy between them. Understanding vacuum energy is crucial for explaining phenomena like dark energy and the accelerated expansion of the universe. The relationship between quantum gravity and dark energy is particularly compelling. Dark energy is thought to arise from the energy of the quantum vacuum, but its observed magnitude is far smaller than theoretical predictions, a discrepancy known as the cosmological constant problem. Quantum gravity might provide a solution by offering a more accurate description of how vacuum energy interacts with spacetime. Resolving this issue would be a major breakthrough, as it would connect the quantum and cosmological scales in a coherent framework. In addition to its theoretical implications, quantum gravity has practical significance for fields like astrophysics and particle physics. For example, understanding the quantum nature of black holes could inform the search for new particles or phenomena in high-energy environments, such as the centers of galaxies or the early universe. Similarly, insights into the quantum structure of spacetime could improve the precision of gravitational wave detectors, enabling us to probe the universe with unprecedented sensitivity. One of the most exciting frontiers in quantum gravity research is the study of quantum cosmology, which seeks to understand the universe's origin and large-scale structure through quantum principles. Quantum cosmology suggests that the universe's initial conditions were governed by quantum fluctuations, which set the stage for the formation of galaxies, stars, and planets. These fluctuations are imprinted on the cosmic microwave background radiation, providing a snapshot of the universe's infancy. By studying these imprints, scientists hope to uncover clues about the quantum nature of spacetime. Quantum gravity also raises questions about the ultimate fate of the universe. Current observations suggest that the universe is expanding at an accelerating rate, driven by dark energy. If this expansion continues indefinitely, it could lead to a big freeze, where galaxies drift apart and stars burn out, leaving a cold, dark cosmos. Alternatively, the universe might undergo a big rip, where the accelerating expansion tears apart galaxies, stars, and even atoms. Quantum gravity could help determine which of these scenarios is most likely by providing a more complete understanding of the forces driving cosmic evolution. The pursuit of quantum gravity is not without challenges. One major obstacle is the lack of experimental evidence, as phenomena at the Planck scale are far beyond the reach of current technology. However, researchers are exploring creative ways to test quantum gravity's predictions indirectly. For instance, some experiments aim to detect tiny deviations from classical physics in high-energy collisions or gravitational wave patterns. Others focus on the behavior of particles in extreme environments, such as neutron stars or black hole mergers, where quantum gravity effects might be more pronounced. Despite these challenges, the quest for quantum gravity continues to inspire scientists, philosophers, and the public alike. It represents a bold attempt to answer some of the deepest questions about the universe, from its origin and structure to its ultimate destiny. By bridging the gap between quantum mechanics and general relativity, quantum gravity has the potential to transform our understanding of reality and our place within it. The journey toward quantum gravity is a testament to the power of human curiosity and ingenuity. It reminds us that the universe is far more complex and mysterious than we can currently comprehend, and that every new discovery brings us closer to the truth. As we continue to explore this frontier, we are not only expanding our knowledge of the cosmos but also deepening our appreciation for the interconnectedness of all things. The interconnectedness revealed by quantum gravity touches on some of the most profound philosophical questions about the universe. If space-time, matter, and energy are all part of an interwoven quantum fabric, then perhaps everything we observe is connected in ways we cannot yet fully understand. This idea aligns with the principle of entanglement in quantum mechanics, where particles can influence each other instantaneously, regardless of the distance separating them. Could this principle extend to the cosmic scale, linking phenomena across the universe through quantum gravitational effects? These are the kinds of questions that drive researchers forward. Entanglement, a cornerstone of quantum mechanics, is also a key concept in the study of black holes within the framework of quantum gravity. One of the most significant breakthroughs in this area came with the realization that black holes might not destroy information, as once feared. According to the principles of quantum mechanics, information about the state of a system cannot be lost, even if that system falls into a black hole. This idea led to the famous black hole information paradox, which remains one of the most debated topics in theoretical physics. The holographic principle, a concept born from quantum gravity research, offers a potential resolution to this paradox. It suggests that all the information contained within a black hole could be encoded on its event horizon, the boundary beyond which nothing can escape. This means that a black hole might function like a cosmic hard drive, storing information about everything it has absorbed. Furthermore, the holographic principle implies that our three-dimensional universe might itself be a projection of two-dimensional information encoded on a distant boundary. This mind-bending idea challenges our very perception of reality and offers a new lens through which to view the cosmos. The holographic principle is deeply tied to string theory, one of the leading candidates for a theory of quantum gravity. String theory proposes that all particles and forces arise from the vibrations of tiny, one-dimensional strings. These strings exist in a higher dimensional space, with additional dimensions compactified into shapes too small to observe directly. While string theory has yet to produce definitive experimental evidence, it provides a mathematically consistent framework for unifying quantum mechanics and general relativity. Its implications, from the multiverse hypothesis to the nature of time, continue to provoke both excitement and skepticism. Another approach to quantum gravity, loop quantum gravity, takes a different route by focusing on the discrete structure of spacetime. In this theory, spacetime is composed of tiny, indivisible units called spin networks, which evolve over time to create the continuum we perceive. Loop quantum gravity offers intriguing insights into the nature of black holes and the Big Bang. For example, it suggests that the singularity at the center of a black hole or at the beginning of the universe might be replaced by a quantum bridge, connecting to another region of spacetime. This idea opens the door to speculative scenarios like the existence of parallel universes or a cyclic cosmos. The cyclic universe model, supported by some interpretations of quantum gravity, posits that the universe undergoes endless cycles of expansion and contraction. Each Big Bang is followed by a Big Crunch, only to be reborn again. This model challenges the traditional view of a singular beginning and suggests that the cosmos might be eternal, with no ultimate beginning or end. Quantum gravity also has profound implications for understanding the arrow of time. In classical physics, time is reversible, meaning the equations work the same whether time moves forward or backward. However, in our everyday experience, time flows in one direction, from past to future. This asymmetry, known as the arrow of time, is closely tied to the second law of thermodynamics, which states that entropy, or disorder, tends to increase over time. Quantum gravity might offer new insights into why time flows as it does, potentially revealing connections between the microscopic world of particles and the macroscopic world of thermodynamics. One speculative idea is that the arrow of time could emerge from the quantum properties of spacetime itself. If spacetime is granular and dynamic, as suggested by quantum gravity, then the flow of time might arise from the interactions of these fundamental units. Alternatively, time might be an emergent property of entanglement, with the direction of time reflecting the spread of quantum correlations. These ideas are still in their infancy, but they highlight the potential of quantum gravity to transform our understanding of time and causality. Quantum gravity also intersects with the study of dark matter and dark energy, two of the most mysterious components of the universe. Dark matter, which makes up about 27% of the universe's mass energy content, interacts with normal matter through gravity but not electromagnetism, making it invisible to telescopes. Dark energy, accounting for about 68% of the universe's energy, is driving the accelerated expansion of the cosmos. Quantum gravity might provide new insights into these phenomena by revealing how they interact with spacetime at the smallest scales. For example, some theories suggest that dark matter could be composed of exotic particles that arise naturally within quantum gravity frameworks. Alternatively, dark energy might be linked to the vacuum energy of spacetime, as described earlier. Understanding these connections could revolutionize cosmology and lead to new ways of detecting and studying dark matter and dark energy. The search for quantum gravity also raises ethical and philosophical questions about the nature of scientific inquiry. Should we prioritize theories with strong mathematical beauty, like string theory, even if they lack direct experimental evidence? Or should we focus on approaches with testable predictions, even if they are less elegant? These debates reflect broader tensions within the scientific community about the balance between theory and observation, creativity and rigor. Despite these challenges, the pursuit of quantum gravity embodies the human spirit of exploration and discovery. It represents our desire to understand the universe at its deepest level, to uncover the principles that govern reality, and to answer age-old questions about our place in the cosmos. Whether or not we ever achieve a complete theory of quantum gravity, the journey itself is a testament to the power of human curiosity and imagination. The exploration of quantum gravity continues to push the boundaries of human knowledge, presenting opportunities for discovery that transcend the limits of our current understanding. One of the most fascinating aspects of this field is its potential to redefine how we view the fabric of reality itself. If spacetime is not a continuous entity but instead consists of discrete, quantized units, this challenges the very foundation of classical physics and our everyday experiences. These quantized units of spacetime, often referred to as Planck-scale structures, are unimaginably small, on the order of meters. At such scales, the familiar concepts of distance and time may lose their meaning, replaced by a more fundamental description of reality. Some researchers liken this to the pixels on a screen. From a distance, the image appears smooth, but up close, it is composed of individual, discrete points. Similarly, our smooth perception of spacetime may emerge from the interactions of these tiny building blocks. This granular view of spacetime has profound implications for understanding black holes. If spacetime is quantized, then the event horizon of a black hole, the boundary beyond which nothing can escape, might not be a smooth surface but rather a complex, dynamic structure. This could provide new insights into the mysterious processes occurring at the edge of black holes, such as the emission of Hawking radiation. Hawking radiation, a phenomenon predicted by Stephen Hawking in 1974, arises from quantum effects near the event horizon. According to quantum mechanics, pairs of virtual particles constantly pop into and out of existence. Near a black hole, one particle in such a pair might fall into the event horizon while the other escapes, creating the appearance of radiation emanating from the black hole. Over time, this process could cause the black hole to lose mass and eventually evaporate completely. The study of Hawking radiation provides a unique testing ground for theories of quantum gravity, as it involves both quantum mechanics and general relativity. The implications of black hole evaporation extend far beyond astrophysics. If information is preserved during this process, as suggested by the principles of quantum mechanics, then black holes could serve as natural laboratories for studying the fundamental nature of information. This ties into the broader concept of quantum information theory, which seeks to understand how information is stored, transmitted, and transformed in the quantum realm. Quantum information theory has practical applications as well. Technologies like quantum computing and quantum cryptography rely on principles of quantum mechanics to perform tasks that are impossible with classical systems. These technologies are not just theoretical. They are already beginning to revolutionize fields like secure communication, optimization, and artificial intelligence. The development of quantum gravity could further enhance these technologies by providing a deeper understanding of the quantum principles that underlie them. One particularly intriguing concept in quantum gravity is the idea of space-time foam. Proposed by physicist John Wheeler, space-time foam describes the notion that at the Planck scale, space-time is not smooth but instead fluctuates wildly due to quantum effects. These fluctuations could give rise to tiny, transient wormholes or other exotic phenomena, creating a dynamic, ever-changing landscape at the smallest scales. If space-time foam exists, it could have observable consequences, such as subtle distortions in the paths of particles or the polarization of light from distant cosmic sources. Detecting these effects would be incredibly challenging, but advances in observational techniques, such as gravitational wave astronomy, might make it possible in the future. Gravitational waves, ripples in space-time caused by massive cosmic events, have already opened a new window into the universe, allowing scientists to study phenomena like black hole mergers and neutron-star collisions. These observations could one day provide clues about the quantum nature of space-time. Another area where quantum gravity could leave its mark is the early universe. The Big Bang represents a singularity, a point where the density of matter and energy becomes infinite, and the laws of physics as we know them break down. Understanding this singularity requires a theory that unifies quantum mechanics and general relativity. Quantum gravity could provide the tools to peer beyond the Big Bang, revealing what, if anything, existed before it. One possibility is that the Big Bang was not the beginning of everything but rather a transition from a previous phase of the universe. In some models, the universe undergoes cycles of expansion and contraction, with each Big Bang marking the start of a new era. Other models suggest that our universe could have emerged from a quantum fluctuation in a larger multiverse. These ideas are speculative but offer tantalizing glimpses into the potential origins of our cosmos. The study of quantum gravity also intersects with questions about the nature of consciousness and reality. If the universe is fundamentally quantum in nature, what does that mean for our understanding of the mind? Some researchers have speculated that consciousness might be linked to quantum processes in the brain, although this idea remains highly controversial. Nevertheless, the quest to understand quantum gravity challenges us to think deeply about the relationship between the observer and the observed, the subjective and the objective. Quantum gravity is not just a scientific endeavor, it is also a deeply philosophical one. It forces us to confront the limits of our knowledge and to grapple with questions that have fascinated humanity for millennia. What is the nature of existence? What lies beyond the observable universe? Are there ultimate laws of physics, or is the cosmos inherently unpredictable? As researchers continue to explore these questions, they are guided by the principle that science is a journey, not a destination. Every discovery raises new questions, and every answer deepens the mystery. The pursuit of quantum gravity exemplifies this process, demonstrating the power of human curiosity and the boundless potential of the human mind. The pursuit of quantum gravity is not just an intellectual exercise but a practical challenge that requires innovative new tools and experimental techniques. To reconcile quantum mechanics and general relativity, scientists must develop new ways to probe the very fabric of space-time itself. The tools we currently have at our disposal, while powerful, are not sufficient to observe the minuscule scales where quantum gravity effects would manifest. One promising approach involves the study of high-energy physics, particularly through particle accelerators like the Large Hadron Collider, LHC. These experiments can create conditions that simulate the extreme energies and densities found in the early universe, allowing scientists to test theories of quantum gravity indirectly. However, the energy scales required to directly observe quantum gravitational effects are far beyond the capabilities of current accelerators, meaning that scientists will likely need to explore more creative approaches to testing these ideas. In recent years, the field of observational cosmology has provided some hope for progress. Instruments like the James Webb Space Telescope, JWST, which is capable of observing the faintest signals from the distant universe, could provide valuable data that might reveal clues about the nature of quantum gravity. For example, the JWST's ability to study the cosmic microwave background (CMB), the afterglow of the Big Bang, could help scientists probe the conditions of the early universe. Any deviations from the expected pattern could indicate quantum gravitational effects at work, potentially offering a direct observation of quantum gravity in action. Gravitational wave astronomy is another rapidly advancing field that may hold the key to unlocking the mysteries of quantum gravity. Gravitational waves are ripples in space-time caused by massive objects like black holes and neutron stars. By studying these waves, scientists can learn about the warping of space-time under extreme conditions and, in doing so, gain insight into the nature of gravity at the quantum level. The detection of gravitational waves has already opened up new frontiers in astrophysics, allowing us to observe events that were previously invisible. Future advancements in this field, particularly with the next generation of detectors like LISA, Laser Interferometer Space Antenna, could provide us with the first direct evidence of quantum gravitational phenomena. However, even with the best technology and most precise instruments, we are still a long way from fully understanding quantum gravity. One of the major obstacles lies in the fact that the theory itself remains incomplete. While string theory, loop quantum gravity, and other approaches provide frameworks for thinking about quantum gravity, none of them has yet produced a definitive, universally accepted description of the quantum nature of space-time. Until such a theory is developed, we will be left with a patchwork of ideas, each offering a different perspective on the true nature of the universe. One of the most exciting aspects of this ongoing research is the way in which different approaches to quantum gravity might complement each other. Rather than viewing these theories as competing, many scientists believe that they could provide different pieces of the puzzle. For example, string theory, which posits that the fundamental building blocks of the universe are tiny, vibrating strings, could offer insights into the quantum structure of space-time. At the same time, loop quantum gravity, which focuses on the quantization of space-time itself, might provide a more direct way to test the effects of quantum gravity in the real world. String theory is particularly notable for its potential to unify all of the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single, coherent framework. This idea, known as the theory of everything, has been a holy grail of physics for decades. While string theory has not yet been fully developed, its promise of a unified description of the universe is one of the reasons why it has garnered so much attention in the scientific community. On the other hand, loop quantum gravity offers a more direct approach to quantizing spacetime. This theory suggests that spacetime is composed of discrete loops of quantum fields, which could provide a more tangible way to test the effects of quantum gravity. One of the most promising predictions of loop quantum gravity is the concept of space-time foam, a chaotic, fluctuating structure at the smallest scales. If space-time is indeed granular in nature, it could have profound implications for our understanding of black holes, the early universe, and the fundamental nature of reality. While these two approaches may seem radically different, they are not necessarily incompatible. Some researchers believe that a complete theory of quantum gravity might require elements from both string theory and loop quantum gravity. Such a theory could provide a more comprehensive understanding of the universe, bridging the gap between the smallest and largest scales. Ultimately, the search for quantum gravity is about more than just solving a scientific puzzle. It is about understanding the fundamental nature of reality itself. If we can uncover the true nature of space-time, we may be able to answer some of the most profound questions in science. What is the origin of the universe? What happens inside a black hole? Can we truly unify all the forces of nature? These questions have fascinated humanity for centuries, and the answers could reshape our understanding of the cosmos. As the field of quantum gravity continues to evolve, it is likely that new ideas and breakthroughs will emerge. We may discover entirely new principles of physics that challenge our preconceived notions of space, time, and reality. The journey toward a theory of quantum gravity is not just a quest for knowledge, it is an exploration of the deepest mysteries of the universe, a journey that will continue to inspire generations of scientists and thinkers for years to come. As the search for a unified theory of quantum gravity continues, it's essential to understand that the journey is not just about developing new models and equations, it's about transforming our entire perspective on the universe. The quest for quantum gravity has already changed the way we think about time, space, and the fundamental nature of reality. But it also has the potential to alter the very fabric of how we understand existence itself. One of the most radical implications of quantum gravity is the possibility that space and time are not static, immutable entities. In classical physics, we think of time as a continuous progression, and space as the unchanging backdrop against which events unfold. However, in the quantum realm, both space and time may be dynamic and malleable, governed by the same quantum principles that dictate the behavior of particles. This challenges our conventional understanding and calls into question the very foundations of how we experience the world around us. The notion of time itself, particularly in the context of quantum gravity, is one of the most mind-bending concepts that researchers are grappling with today. In the framework of quantum mechanics, time often appears as a parameter, something that progresses uniformly and predictably. But when you combine quantum mechanics with general relativity, the behavior of time becomes far more complex. In Einstein's theory of general relativity, time is inextricably linked to the fabric of space itself. Space-time is a four-dimensional continuum, where mass and energy warp the fabric of space-time, causing it to bend and stretch. This curvature of space-time is what we perceive as gravity. As objects move through space-time, their trajectories are influenced by the curvature, and time itself can stretch or contract depending on the gravitational field. Near massive objects like black holes, the curvature becomes extreme, and time slows down. But in quantum gravity, the rules may change entirely. Time could become a more fluid concept, one that fluctuates at the smallest scales in a manner similar to how the position of particles is described by probability waves. At the Planck scale, time might be discrete rather than continuous, existing in tiny, indivisible units, similar to how energy levels are quantized in atoms. If this is the case, the smooth passage of time that we experience in our everyday lives could be an illusion, an emergent phenomenon that arises from the interactions of fundamental quantum processes. Another aspect of time that quantum gravity might help to explain is the so-called arrow of time. In our everyday experience, time seems to flow in one direction, from the past through the present and into the future. This is a result of the second law of thermodynamics, which states that the entropy, or disorder, of a closed system always increases over time. The increase in entropy gives time its direction, as systems naturally move toward more disordered states. However, the fundamental equations of physics, including those in quantum mechanics, are typically time-symmetric. They don't favor one direction of time over another. This has led to the question, why does time seem to flow in only one direction? Quantum gravity may offer an explanation for this puzzle. Some theories suggest that the arrow of time is tied to the growth of complexity in the universe, or to the way in which quantum systems evolve. As space-time itself becomes more quantized, at the smallest scales, the flow of time might be better understood as a fundamental feature of the universe, one that emerges from the behavior of quantum fields. The development of quantum gravity also raises profound questions about the nature of space. We are accustomed to thinking of space as an infinite, continuous expanse, an ever-present stage upon which all physical events unfold. But as quantum gravity suggests, space may not be continuous at all. Instead, it might consist of discrete, granular, units that are the smallest possible building blocks of reality. This idea echoes the way in which we think of matter. Atoms are composed of indivisible particles, and these particles are composed of smaller components like quarks and leptons. Similarly, space could be composed of fundamental, space-time atoms, that form the foundation of the universe. If this theory holds, the very concept of distance may need to be reconsidered. If space is quantized, then measuring distances at extremely small scales would not yield smooth, continuous results. Instead, measurements might reveal a pixelated structure, where the smallest possible distance is determined by the Planck length. This could radically alter our understanding of geometry, making it necessary to rethink concepts like curvature, geodesics, the paths that objects follow through spacetime, and the nature of physical forces. This idea of a discrete structure for space and time also has important consequences for our understanding of black holes. In classical physics, black holes are regions of spacetime where the gravitational pull is so intense that not even light can escape. They are described by the equations of general relativity, which predict that a black hole contains a singularity, a point of infinite density and zero volume, at its center. This singularity represents a breakdown of the laws of physics, as the density becomes infinite and the curvature of spacetime becomes infinitely steep. However, in the framework of quantum gravity, this singularity might not exist in the way we think. The quantization of spacetime could prevent the formation of an actual singularity, replacing it with a more complex structure that avoids infinite density. The quantum nature of spacetime might provide a smoothing effect that prevents the extreme conditions predicted by general relativity. This would have profound implications for the physics of black holes, potentially resolving the paradoxes associated with them. For example, one of the most famous paradoxes in black hole physics is the information paradox. According to quantum mechanics, information about the state of a system must always be conserved, even if the system undergoes extreme transformations. However, general relativity suggests that once something crosses the event horizon of a black hole, it is lost forever, along with any information it contains. This creates a contradiction, as quantum mechanics would imply that the information should be recoverable. Quantum gravity theories, such as those involving string theory or loop quantum gravity, may provide a resolution to this paradox. Some models suggest that the information is not lost inside a black hole but is instead encoded in a way that is consistent with quantum principles. For instance, the information could be stored on the event horizon itself or could be transferred to a higher dimensional space. The details are still unclear, but the potential to resolve this paradox represents a major breakthrough in our understanding of both black holes and quantum mechanics. As we continue to explore the mysteries of quantum gravity, it becomes clear that the challenges are as much philosophical as they are scientific. Quantum gravity forces us to reconsider our most fundamental assumptions about reality. Are space and time truly continuous, or are they fundamentally discrete? Does time flow in a straight line, or is it more fluid and dynamic than we can imagine? Are black holes gates to another universe, or are they simply complex regions of distorted spacetime? These questions push us to the limits of human comprehension, forcing us to confront the nature of existence itself. As we continue to delve deeper into the complexities of quantum gravity, the significance of these questions cannot be overstated. Every new piece of knowledge we uncover in this field challenges our very perception of reality, urging us to rethink what we thought we knew about the universe. One of the most intriguing aspects of quantum gravity is how it might finally unite two of the most powerful and successful theories in physics: quantum mechanics and general relativity. These two pillars of modern physics have long been seen as separate and incompatible. Quantum mechanics describes the behavior of subatomic particles, tiny, probabilistic, and governed by uncertainty. Meanwhile, general relativity describes the force of gravity at large scales, such as planets, stars, and galaxies, where spacetime is curved by the presence of mass and energy. The problem arises because, while both theories are incredibly successful in their respective domains, they fundamentally differ in how they treat space, time, and matter. General relativity views space and time as smooth, continuous entities, whereas quantum mechanics deals with probabilities and uncertainties at the smallest scales. The quest for quantum gravity is an attempt to reconcile these two approaches and create a unified theory that can explain the behavior of both the very small and the very large. A central challenge in this quest is the incompatibility of the two theories when applied to extreme environments, such as black holes or the Big Bang. In these conditions, the forces of gravity are immense, and space-time is severely curved, yet quantum effects, such as particle wave duality, uncertainty, and entanglement, also play a crucial role. How do we account for both the curvature of space-time and the probabilistic nature of quantum mechanics in a single framework? This question becomes even more pressing when we consider phenomena such as the inside of black holes. According to general relativity, when something falls into a black hole, it is crushed to an infinitely dense point at the singularity, where space-time curvature becomes infinite. However, quantum mechanics predicts that particles cannot exist at such infinite densities. Something is clearly wrong with our current understanding, suggesting that new physics, perhaps a theory of quantum gravity, will be required to resolve the contradictions. One possible approach to merging quantum mechanics and general relativity is through the concept of quantum space-time. In this framework, space-time itself is not a smooth continuum, as described by general relativity, but is instead quantized, much like matter and energy. This means that at the smallest scales, the Planck scale, space-time could consist of discrete, indivisible units, or quantum chunks. These quantum units of space-time might be so tiny that they are currently beyond our ability to observe directly, but their effects could be detectable through indirect means, such as their influence on the behavior of particles or the structure of the universe. This idea is central to several quantum gravity theories, including loop quantum gravity and string theory. Loop quantum gravity proposes that space-time is composed of tiny loops, or spin networks, which are interconnected in a way that gives rise to the smooth space-time we observe at larger scales. String theory, on the other hand, posits that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings exist in higher dimensional spaces, and their vibrations give rise to the particles and forces we observe. Both of these approaches have the potential to unify quantum mechanics and general relativity, but they are still in the early stages of development. Researchers are still working to understand how these theories might explain phenomena such as black holes, the Big Bang, and the behavior of space-time at extremely small scales. For example, in the case of black holes, quantum gravity might provide a solution to the information paradox, which has been a long-standing puzzle in theoretical physics. According to classical general relativity, when something falls into a black hole, it is lost forever, and the information about its state is destroyed. This contradicts the principles of quantum mechanics, which state that information must always be conserved. The idea that quantum gravity might provide a way for this information to be preserved, perhaps encoded on the event horizon of the black hole or stored in a higher dimensional space, has opened up new avenues of research and speculation. At the same time, quantum gravity could help explain the very origins of the universe itself. The Big Bang theory, which describes the origin of the universe from a singularity, presents a major challenge for both general relativity and quantum mechanics. According to general relativity, the universe began as an infinitely dense point, but quantum mechanics suggests that particles cannot exist at infinite density. The resolution of this paradox could come from a quantum theory of gravity that explains how the Big Bang unfolded and how the laws of physics changed in the earliest moments of the universe. Beyond these grand cosmic phenomena, quantum gravity also has implications for the structure of space-time on more local scales. For example, the idea of space-time foam suggests that at the smallest scales, space-time is highly turbulent, with tiny fluctuations occurring constantly. These fluctuations could have observable effects on the behavior of particles and the propagation of light. Understanding these fluctuations could help us probe the very fabric of the universe and test the predictions of quantum gravity. The search for quantum gravity is also opening up new avenues of experimental research. One of the most exciting prospects in this area is the study of gravitational waves. These ripples in spacetime, first predicted by Einstein's theory of general relativity, were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves carry information about the structure of spacetime itself, and by studying them, scientists hope to gain insights into the behavior of quantum gravity. In particular, gravitational waves from events like black hole mergers or neutron-star collisions might provide clues about the nature of spacetime at extreme scales. If quantum gravity is correct, these waves should behave in ways that differ from the predictions of general relativity. Detecting these subtle differences could provide a direct test of quantum gravity theories and bring us one step closer to understanding the true nature of the universe. Another experimental approach to testing quantum gravity is the study of high-energy cosmic phenomena. For example, cosmic rays, particles from space that travel at nearly the speed of light, could provide information about the structure of spacetime at very small scales. By studying how these particles interact with the universe, scientists hope to detect signatures of quantum gravitational effects. Despite the challenges, the potential rewards of understanding quantum gravity are immense. If we can successfully merge quantum mechanics and general relativity into a single, unified theory, it would represent one of the greatest achievements in the history of science. It would provide us with a deeper understanding of the universe's most mysterious phenomena, from the behavior of black holes to the origins of the universe itself. And it would help us answer some of the most profound questions about the nature of reality. As the search for quantum gravity continues, we are reminded that the universe is far more complex and strange than we can even imagine. The answers may lie in the smallest of scales, hidden within the fabric of spacetime itself. But with each new discovery, we move one step closer to unraveling the deepest mysteries of the cosmos. The pursuit of quantum gravity is not just an academic endeavor. It is one that has profound implications for our understanding of reality. It touches on everything from the deepest mysteries of the universe to the most fundamental aspects of the nature of space, time, and existence. But perhaps the most exciting and puzzling part of this quest is the recognition that the more we learn, the more we realize we don't yet know. Quantum gravity could hold the key to unifying the forces of nature, revealing a deeper, more intricate picture of how the universe operates. As scientists strive to construct a theory of quantum gravity, they must grapple with an enormous range of paradoxes, each one more mind-boggling than the last. How do we account for the fact that gravity, as described by general relativity, is a continuous force, yet quantum mechanics tells us that everything in the universe is discrete, made up of indivisible particles and waves? How do we reconcile the curved, four-dimensional spacetime of general relativity with the probabilistic wave functions of quantum mechanics? How do we describe the behavior of matter and energy in the extreme environments near black holes or during the Big Bang, where both quantum and gravitational effects are at their most intense? At the heart of these challenges lies the fact that the theories of quantum mechanics and general relativity operate on entirely different principles. Quantum mechanics describes the behavior of particles on the smallest scales, where the laws of probability govern their interactions. It tells us that particles can exist in multiple states simultaneously, that they can be entangled over vast distances, and that their behavior is fundamentally unpredictable. In contrast, general relativity describes the force of gravity and the curvature of spacetime at much larger scales. It tells us that space and time are smooth, continuous, and can be shaped by mass and energy. Both of these theories have been confirmed through extensive experimental evidence, yet they operate in fundamentally different realms. So, the problem is clear: how do we reconcile them? The answer may lie in the concept of quantum spacetime, a new understanding of the very structure of the universe itself. Quantum spacetime suggests that, rather than being a continuous fabric, spacetime could be composed of discrete units, or quantum chunks, which would behave in ways that differ drastically from our everyday experiences. This could mean that at the smallest scales, at the Planck length, space and time are no longer smooth, but are instead subject to quantum fluctuations, which are far beyond our ability to observe directly. It is a radical shift in our thinking about the nature of reality, one that challenges the very foundations of physics as we know it. To explore this further, let's return to one of the central challenges of quantum gravity: black holes. Black holes are some of the most mysterious objects in the universe, and their study has provided key insights into the nature of gravity and the limits of our current understanding of physics. According to general relativity, when a massive object collapses under its own gravity, it can form a black hole, a region of spacetime where the gravitational pull is so strong that not even light can escape. At the center of a black hole lies a singularity, a point where the curvature of spacetime becomes infinite, and all known laws of physics break down. But this description of black holes raises a fundamental problem. Quantum mechanics tells us that no information can be lost in the universe. Information about the state of a system must always be preserved, even if it undergoes a transformation. Yet, according to general relativity, once something falls into a black hole, it is lost to the outside world. This paradox, the so-called information paradox, has plagued physicists for decades. How can information be lost in a black hole without violating the principles of quantum mechanics? Quantum gravity theories offer possible resolutions to this paradox. One of the most promising ideas is that the information may not be lost, but rather encoded in some form on the event horizon of the black hole, the boundary that separates the inside of the black hole from the outside universe. This idea is known as the holographic principle, and it suggests that the information about a three-dimensional object can be encoded on a two-dimensional surface. If this principle holds true for black holes, then the information that falls into them could be preserved, albeit in a form that is vastly different from our usual understanding. This idea leads us to the fascinating possibility that the event horizon of a black hole could serve as a kind of cosmic computer, encoding information about everything that falls into it. The implications of this idea are profound, as they suggest that the fabric of spacetime itself may be capable of processing and storing information in ways we cannot yet comprehend. The search for quantum gravity, then, is not just about understanding the fundamental forces of nature. It is also about unlocking the mysteries of how information is stored and transmitted throughout the universe. Another important aspect of quantum gravity is the way it might help us understand the origins of the universe itself. The Big Bang Theory, which describes the birth of the universe from an infinitely dense point, raises similar questions to those posed by black holes. How did the universe begin, and what happened in the earliest moments of its existence? According to general relativity, the universe began as a singularity, a point of infinite density and temperature, where the laws of physics break down. But quantum mechanics tells us that such a state is not physically possible, as it violates the principle that particles cannot exist at infinite density. This conflict between general relativity and quantum mechanics is at the heart of the search for quantum gravity. The theory of quantum gravity might offer a way to reconcile these two descriptions of the universe, providing a new understanding of the Big Bang and the origins of the cosmos. One possible solution is the idea of a quantum bounce, in which the universe does not begin with a singularity, but instead undergoes a bounce from a previous state. This idea suggests that the universe could be part of a cyclical process, where it expands and contracts in a never-ending cycle, with each bounce marking the beginning of a new phase of cosmic evolution. While these ideas are still speculative, they highlight the potential of quantum gravity to reshape our understanding of the universe's beginnings. If quantum gravity can explain the behavior of the universe at the moment of the Big Bang, it could open the door to new insights into the fundamental nature of space, time, and reality itself. As we push forward in the search for quantum gravity, the potential rewards are immense. The discovery of a unified theory that merges quantum mechanics and general relativity would be a landmark achievement in the history of science, providing a deeper understanding of the universe's most mysterious phenomena. It would offer new insights into the behavior of black holes, the nature of spacetime, and the origins of the cosmos. And it would help us answer some of the most profound questions about the nature of reality, such as, what is the true nature of time? Can we travel through time? How did the universe come into being, and where is it headed? But even as we make strides toward a theory of quantum gravity, we must remember that there is still much we do not know. The universe is full of mysteries, and the search for answers is ongoing. Perhaps the most exciting aspect of this journey is that, with each new discovery, we come one step closer to understanding the deepest secrets of existence. The road ahead in the search for quantum gravity is long and uncertain, but it's also brimming with potential discoveries that could change everything we know about the universe. One of the most intriguing aspects of this journey is that, despite all of our advancements, we are still nowhere near a complete understanding. Every time we think we're getting closer, new mysteries emerge. And the pursuit of quantum gravity is perhaps the biggest and most challenging of these mysteries. As we continue to develop theories and experimental techniques, physicists are increasingly turning to more abstract mathematical models to guide their research. The mathematical framework of quantum gravity is incredibly complex, often involving ideas and concepts that are far beyond our everyday experience. This is a key reason why quantum gravity is such a difficult concept to grasp. The tools we use to describe it are not intuitive and often defy our common sense notions of reality. However, it is through these mathematical models that we are beginning to see glimpses of how quantum gravity might work, and what it could reveal about the nature of spacetime and the universe. One of the leading approaches to quantum gravity is string theory. This theory proposes that the most fundamental building blocks of nature are not point-like particles, as described by traditional particle physics, but rather tiny, vibrating strings of energy. These strings are thought to vibrate at different frequencies, and the different modes of vibration correspond to different particles. String theory offers a framework that could potentially unite all of the fundamental forces of nature, including gravity, into a single, unified theory. String theory is compelling because it naturally incorporates the principles of both quantum mechanics and general relativity. In string theory, the force of gravity is explained through the exchange of gravitons, hypothetical particles that mediate the gravitational force. This allows string theory to incorporate gravity into the quantum mechanical framework in a way that does not violate the principles of either theory. In other words, string theory might be able to reconcile the small, quantum world with the large, relativistic world in a way that no other theory has yet been able to do. However, string theory is not without its challenges. One of the most significant is that it operates in a higher dimensional framework, where spacetime is not just the familiar 3 dimensions of space and 1 of time, but instead involves many more dimensions, up to 11 in some versions of the theory. These extra dimensions are theorized to be compactified, meaning they are curled up in such a way that they are effectively invisible at the macroscopic scale. While these extra dimensions help to solve some of the problems in reconciling quantum mechanics and general relativity, they also introduce a level of complexity that makes the theory difficult to test experimentally. One promising direction in string theory is the idea of holography. The holographic principle suggests that the information contained within a region of space can be encoded on its boundary. This principle has gained a lot of attention in recent years, particularly in the study of black holes, where it might offer a solution to the information paradox. The idea is that the 3-dimensional information about a black hole, or even the entire universe, could be encoded on a 2-dimensional surface, much like the way a hologram encodes 3-dimensional images in 2 dimensions. This concept could also be applied to quantum gravity, where the fundamental structure of spacetime might be described as a holographic projection of lower-dimensional information. Another approach that has gained traction in recent years is loop quantum gravity. This theory proposes that spacetime itself is quantized, made up of discrete loops of energy. In this framework, the smooth, continuous spacetime described by general relativity is replaced with a network of loops that make up the very fabric of the universe. These loops are thought to be incredibly small, with lengths on the order of the Planck length, which is about 10 to the power of -35 meters. This idea stands in contrast to the traditional view of spacetime as a continuous fabric, and instead suggests that spacetime is fundamentally discrete at the smallest scales. Loop quantum gravity has been able to produce some remarkable results, particularly in the study of black holes and the Big Bang. One of the most exciting aspects of loop quantum gravity is its ability to resolve the singularity at the center of a black hole. In general relativity, the singularity represents a point where spacetime curvature becomes infinite, and all known laws of physics break down. But in loop quantum gravity, the quantization of spacetime prevents the curvature from becoming infinite, effectively eliminating the singularity, and allowing for a more complete description of black holes. Similarly, loop quantum gravity offers a potential solution to the problem of the Big Bang's singularity. According to the theory, the Big Bang was not a true singularity, but rather a quantum bounce, where the universe went through a transition from a contracting state to an expanding one. This idea suggests that the universe may have existed in some form before the Big Bang, and that the current expansion is just one phase in a never-ending cycle of cosmic rebirth. This cyclical view of the universe is an exciting possibility, as it would offer a more complete and unified picture of cosmic evolution. Despite these promising results, loop quantum gravity also faces its own set of challenges. One of the most significant is that it has yet to provide a fully detailed, predictive framework for understanding quantum gravity at all scales. While loop quantum gravity is able to describe certain aspects of the quantum nature of spacetime, it still lacks a comprehensive theory that can account for all of the phenomena we observe in the universe. Additionally, loop quantum gravity has not yet been able to produce testable predictions, making it difficult to verify through experiment. As we continue to explore quantum gravity, we must also consider other possible avenues for understanding the fundamental nature of space, time, and gravity. One promising direction is the study of quantum cosmology, which seeks to apply the principles of quantum mechanics to the entire universe. Quantum cosmology aims to describe the behavior of the universe at the earliest moments of the Big Bang, where both quantum and gravitational effects were significant. By studying the quantum properties of the universe as a whole, scientists hope to gain insights into the origin and evolution of the cosmos, and perhaps uncover new laws of physics that could explain the mysteries of quantum gravity. The search for quantum gravity is also leading us to new, innovative ways of thinking about the very nature of reality. It forces us to confront questions that challenge our deepest intuitions, such as, what is the true nature of space? What is time, and does it exist independently of the objects and events within it? How do we reconcile the microscopic world of quantum particles with the macroscopic world of galaxies and black holes? As we search for answers to these questions, we are uncovering a new understanding of the universe, one that is more interconnected, more mysterious, and more awe-inspiring than we could have ever imagined. Quantum gravity is not just a scientific theory, it is a new lens through which we can view the universe and our place within it. It pushes the boundaries of human knowledge and challenges us to think about the cosmos in ways that are truly extraordinary. And while the answers may not come easily or quickly, the journey of discovery is one that promises to reshape our understanding of the most fundamental aspects of existence. As we continue on this path, it is important to remember that the search for quantum gravity is still in its early stages. We have made great strides, but there is much more to learn. Every new theory, every new observation, brings us closer to the truth, but the final answer may still be far off. The universe is vast, and the mysteries it holds are deep. But the pursuit of quantum gravity offers us a glimpse into the very fabric of reality itself, and the potential for profound discoveries that could transform the way we think about everything. The pursuit of quantum gravity is a truly humbling endeavor. It asks us to reconsider the very essence of reality, to question what we think we know, and to push beyond the limits of conventional understanding. Every step forward in this field opens up new challenges and new opportunities for exploration, revealing a universe that is far more complex and intricate than we could have ever imagined. One of the most profound aspects of quantum gravity is its ability to bridge the gap between two realms of physics that have traditionally been seen as separate and incompatible: the tiny, quantum realm of subatomic particles, and the vast, relativistic realm of massive objects and cosmic structures. General relativity and quantum mechanics have been the pillars of modern physics, but for much of the 20th century, they operated in parallel, each describing different aspects of the universe. However, when it comes to the most extreme phenomena, such as black holes and the Big Bang, both quantum effects and gravitational effects are equally important. In these situations, our current understanding breaks down, and we are left with the task of merging these two realms into a single, unified theory. This task is easier said than done. The two theories operate under fundamentally different principles. Quantum mechanics is probabilistic, dealing with particles and waves that exist in a superposition of states until they are measured. It operates on the very smallest scales of the universe, where particles can exist in multiple states at once, and where uncertainty and indeterminacy are not only possible, but fundamental. In contrast, general relativity is deterministic, describing the behavior of massive objects and the curvature of spacetime. It operates on the largest scales, such as those of planets, stars, and galaxies, and it treats spacetime as a smooth, continuous fabric. The conflict between these two theories arises when we try to apply them to situations where both quantum and gravitational effects are significant. Black holes, for example, are regions of spacetime where the gravitational pull is so strong that not even light can escape. At the center of a black hole lies a singularity, a point of infinite density where the laws of physics break down. To understand what happens inside a black hole, we need both the quantum description of matter and the relativistic description of gravity. Yet, when we try to combine these two, the mathematics doesn't work. Something is missing, something that could reconcile these two seemingly incompatible frameworks. This is where quantum gravity comes in. It is the theory that attempts to unify quantum mechanics and general relativity, and in doing so, provide a complete understanding of the most extreme and mysterious phenomena in the universe. However, as we've seen, this is no easy task. The different approaches to quantum gravity, such as string theory, loop quantum gravity, and others, are all grappling with the same fundamental issues: how to merge the quantum and gravitational worlds into a single, coherent framework. String theory, for instance, offers a promising approach by introducing the idea that the fundamental building blocks of nature are not point-like particles, but rather tiny, vibrating strings. These strings exist in a higher dimensional space, which allows them to interact with each other in ways that can potentially explain both quantum phenomena and gravitational effects. String theory's ambition is to provide a unified theory of all the fundamental forces of nature, including gravity. However, its reliance on extra dimensions, up to 11 in some versions, poses a significant challenge. These extra dimensions are not directly observable, making it difficult to test the theory through experiments. On the other hand, loop quantum gravity takes a different approach, focusing on the quantization of spacetime itself. In this theory, spacetime is not a smooth, continuous fabric, but rather a network of discrete loops. These loops are thought to represent the fundamental structure of spacetime at the Planck scale, where quantum effects become significant. This framework has shown promise in resolving some of the paradoxes of general relativity, such as the singularities in black holes and the Big Bang. Loop quantum gravity has also proposed a model for the evolution of the universe that avoids the singularity, suggesting that the Big Bang was not a true beginning but rather a bounce from a previous contraction. While both string theory and loop quantum gravity have made impressive strides in their attempts to reconcile quantum mechanics and general relativity, either has been able to provide a complete, experimentally verifiable description of quantum gravity. This is partly due to the fact that we currently lack the technology to probe the Planck scale directly, where quantum gravitational effects would become apparent. The Planck length, which is about 10 to the power of negative 35 meters, is far smaller than anything we can observe with current technology. This means that, for now, our understanding of quantum gravity is confined to mathematical models and theoretical predictions. Despite these challenges, there are several potential avenues for testing quantum gravity in the future. One of the most promising is the study of black holes. Black holes are natural laboratories for quantum gravity, as they involve both strong gravitational fields and extreme quantum effects. The recent discovery of gravitational waves, for example, has opened up a new way to observe black holes and their interactions. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, and they carry information about the gravitational properties of the objects that generated them. By studying these waves, scientists hope to gain insights into the nature of spacetime and gravity at the quantum level. Similarly, the study of the cosmic microwave background (CMB), the faint afterglow of the Big Bang, may provide another window into the early universe, where quantum gravitational effects would have been significant. The CMB contains information about the state of the universe just a few 100,000 years after the Big Bang, but by looking at its fine details, scientists hope to uncover clues about the quantum nature of spacetime during the very early moments of cosmic evolution. Additionally, experiments at high-energy particle colliders, such as the Large Hadron Collider, LHC, may provide indirect evidence for quantum gravity. While the LHC is not capable of directly probing the Planck scale, it can produce collisions at incredibly high energies that may reveal new physics beyond the standard model. These experiments could help to identify potential signatures of quantum gravitational effects, such as the production of miniature black holes or the detection of extra dimensions. Ultimately, the discovery of a quantum theory of gravity would represent one of the greatest breakthroughs in the history of science. It would not only deepen our understanding of the most fundamental aspects of nature, but also have profound implications for our understanding of the universe as a whole. It could offer new insights into the birth and evolution of the cosmos, the behavior of black holes, the nature of space and time, and the true meaning of gravity itself. The quest for quantum gravity is more than just a scientific endeavor. It is a journey into the heart of the universe's deepest mysteries. And while we may not yet have all the answers, each step forward brings us closer to uncovering the ultimate truth of the cosmos. As we continue this exploration into quantum gravity, it becomes clear that what we are attempting to do is nothing less than redefine our understanding of reality itself. The very fabric of space and time is under scrutiny, and the implications of any new insights could be profound, not just for physics, but for how we view existence. One of the most tantalizing aspects of quantum gravity is how it could reveal new dimensions of space. These extra dimensions are a key prediction of string theory. If they exist, they would not be visible in our everyday experience, but their effects might be detectable in extremely high-energy environments, such as those that could exist near black holes or during the early stages of the universe. In string theory, these dimensions are compactified, meaning that they are curled up into incredibly small spaces, invisible to us unless we can probe them directly. One of the leading ideas in quantum gravity is that these hidden dimensions could play a crucial role in reconciling the forces of nature. For instance, in string theory, gravity is thought to arise from the vibration of strings in these extra dimensions. By incorporating the idea of extra dimensions into quantum theory, we might be able to explain why gravity is so much weaker than the other fundamental forces, such as electromagnetism or the strong nuclear force. This would answer a long-standing question in physics: why gravity, despite being the force that governs the motion of planets and galaxies, is so incredibly weak compared to the other fundamental forces. Loop quantum gravity, on the other hand, doesn't rely on extra dimensions. Instead, it treats space and time as fundamentally quantized. In this theory, space is not a smooth continuum, as described by general relativity, but is made up of tiny, discrete units. These loops of space-time are the basic building blocks of the universe, and they may hold the key to understanding quantum gravity. Loop quantum gravity has the potential to resolve some of the most perplexing issues in theoretical physics, such as the nature of black holes and the singularity at their centers. One of the most exciting aspects of loop quantum gravity is its prediction that space and time may not behave as we expect at the smallest scales. The theory suggests that, at very small scales, close to the Planck length, space-time could become fuzzy or grainy. This means that, instead of being smooth and continuous, space-time might have a discrete structure, with small, indivisible units that can be manipulated. This idea challenges our traditional understanding of the nature of space and time, and could provide a more accurate description of the behavior of the universe at the quantum level. But how can we test these theories? As it stands, testing quantum gravity directly remains one of the greatest challenges in modern physics. The energies required to probe the Planck scale, where quantum gravitational effects would become significant, are far beyond the capabilities of any current or near-future experiment. The Planck length, the scale at which quantum gravity effects are thought to become significant, is so small, about 10 to the power of -35 meters, that it is well beyond our ability to measure. Despite these challenges, there are still ways to indirectly test quantum gravity theories. For example, scientists are beginning to study the behavior of black holes more closely, as these objects are thought to be the perfect testing grounds for quantum gravity. Black holes, with their immense gravity and extreme environments, are one of the few places in the universe where both quantum effects and general relativity are equally important. By observing how matter behaves near black holes, or by studying the radiation emitted from their event horizons, scientists hope to gather clues about the nature of quantum gravity. One of the most important discoveries in this area came in the form of Hawking radiation. In the 1970s, physicist Stephen Hawking proposed that black holes are not entirely black. Instead, they emit radiation due to quantum effects near their event horizons. This radiation, now known as Hawking radiation, could provide a way to study black holes and quantum gravity indirectly. The discovery of Hawking radiation raised the possibility that black holes might eventually evaporate over time, releasing their mass in the form of radiation. This idea has profound implications for our understanding of black holes and quantum gravity, as it suggests that quantum effects can influence even the most massive objects in the universe. Similarly, the study of gravitational waves, which were first detected in 2015, could provide valuable insights into quantum gravity. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as the collision of two black holes. These waves carry information about the dynamics of the objects that produce them, and could provide a new way to test theories of quantum gravity. By studying the details of gravitational waves, scientists hope to uncover clues about the structure of spacetime and the behavior of matter at the most fundamental level. But there is another exciting possibility on the horizon: the study of the early universe itself. The Big Bang represents the ultimate test case for quantum gravity, as it was a time when both quantum effects and gravitational effects were crucial. The very first moments of the universe, right after the Big Bang, represent a regime where both general relativity and quantum mechanics must work together, and where we have little understanding of how the two theories would interact. By studying the cosmic microwave background (CMB), the faint afterglow of the Big Bang, scientists are beginning to probe the earliest moments of the universe. Any tiny fluctuations in the CMB could provide valuable clues about the quantum nature of spacetime during the Big Bang. Moreover, the idea of a multiverse, suggested by certain interpretations of quantum mechanics, adds an intriguing layer to the quantum gravity puzzle. According to some versions of string theory, our universe may be just one of many universes in a vast multiverse. These other universes could have different laws of physics, including different gravitational constants, or even different numbers of dimensions. The study of quantum gravity could not only help us understand the nature of our own universe but also shed light on the possibility of other universes, with entirely different properties and behaviors. The search for quantum gravity is a search for the most fundamental truths of nature. It is a quest to understand the deepest mysteries of space and time, to uncover the true nature of reality itself. Whether through string theory, loop quantum gravity, or some other theory yet to be discovered, the answers we find could revolutionize our understanding of the universe. While we may not yet have all the answers, the journey of discovery is just beginning, and the future of quantum gravity holds the promise of unlocking some of the greatest secrets of the cosmos. The search for a unified theory that incorporates quantum gravity is not just an intellectual exercise. It has the potential to change everything we know about the universe. As we continue to explore these enigmatic concepts, it's clear that the stakes are incredibly high. To understand the deepest layers of reality, we must first reconcile two seemingly incompatible frameworks: the infinitely small and the incomprehensibly large. The current divide between quantum mechanics and general relativity leaves us with an incomplete picture of the universe. While general relativity works wonders on large scales, explaining the motion of planets, stars, and galaxies, quantum mechanics excels at describing the behavior of subatomic particles, revealing the bizarre and counterintuitive nature of the smallest scales. But these two theories have never comfortably fit together, especially in extreme environments like black holes, where gravity is so intense that spacetime itself is warped beyond recognition. Black holes are perhaps the most mysterious objects in the universe, and they offer a rare glimpse into the realms of quantum gravity. According to classical general relativity, black holes contain singularities, points in space where gravity is infinitely strong and space-time curvature becomes infinite. At these points, the laws of physics as we know them break down, and we're left with a paradox. How can we have a singularity where the known laws of physics fail to apply? This question has driven physicists to seek a theory of quantum gravity that might provide a solution. The idea of a black hole singularity raises several profound issues, one of which is the problem of information loss. According to quantum mechanics, information about the state of a system should never be lost. But in the case of a black hole, anything that crosses the event horizon, the boundary beyond which nothing can escape, seems to be lost forever. This creates a paradox known as the black hole information paradox. If black holes destroy information, it would contradict the fundamental principles of quantum mechanics. The quest for quantum gravity could hold the key to resolving this paradox. One possibility that has emerged in recent years is the concept of the firewall of a black hole. Some researchers propose that instead of a smooth event horizon, there could be a boundary layer, known as the firewall, that destroys any incoming information and prevents it from entering the black hole. This idea has sparked heated debates among physicists, as it challenges our basic understanding of space and time. If the firewall theory holds, it would suggest that quantum mechanics and general relativity are far more incompatible than previously thought, requiring a complete overhaul of our understanding of black holes and the nature of spacetime itself. Despite these challenges, quantum gravity also offers hope for solving some of the biggest mysteries in physics. For instance, it might provide an explanation for the behavior of the universe during the Big Bang. The birth of the universe, according to the standard model of cosmology, involved a period of rapid inflation, a sudden and massive expansion that occurred in the first fractions of a second. During this time, quantum fluctuations in the fabric of spacetime could have played a crucial role in shaping the structure of the universe. By studying quantum gravity, we might be able to understand how these fluctuations contributed to the formation of galaxies, stars, and all the structures we see in the universe today. Moreover, quantum gravity could offer new insights into the nature of dark matter and dark energy, two of the most mysterious substances in the universe. Dark matter, which makes up about 27% of the universe's mass, does not emit or absorb light, making it invisible to our current instruments. Dark energy, which is thought to make up around 68% of the universe, is believed to be responsible for the accelerated expansion of the cosmos. These enigmatic phenomena remain largely unexplained by current theories of physics. A theory of quantum gravity could offer new ways to explore these unknowns, potentially revealing new fundamental forces or particles that could explain dark matter and dark energy. One of the most promising areas of research in quantum gravity is the study of the early universe. By analyzing the cosmic microwave background (CMB), the faint radiation left over from the Big Bang, scientists can probe the very early moments of the universe, when quantum effects were most significant. The CMB contains tiny fluctuations that hold clues to the structure of the universe during its infancy. These fluctuations could have been caused by quantum gravitational effects, offering a unique opportunity to study the interaction of quantum mechanics and general relativity in the extreme conditions of the early universe. Another avenue of research is the search for a theory of quantum gravity that can explain the dynamics of spacetime itself. In general relativity, spacetime is treated as a smooth, continuous fabric that can be curved by the presence of mass and energy. But in quantum mechanics, spacetime behaves in a much more erratic and probabilistic way. A theory of quantum gravity could potentially describe how spacetime behaves on the smallest scales, revealing a picture of reality that is vastly different from what we experience on larger scales. One potential model that has attracted significant attention is loop quantum gravity, LQG. This theory suggests that spacetime is not continuous but instead is composed of discrete chunks, or loops, that form the fundamental building blocks of the universe. According to LQG, these loops are the quantum equivalent of the fabric of spacetime, and they give rise to the smooth spacetime that we observe at larger scales. This discrete structure could offer a way to reconcile quantum mechanics with general relativity, providing a unified framework for understanding the forces of nature. However, LQG is not the only contender in the search for a theory of quantum gravity. Another leading candidate is string theory, which proposes that the fundamental building blocks of the universe are not point particles but tiny, vibrating strings. These strings can exist in multiple dimensions, and their vibrations give rise to the forces and particles that we observe in the universe. String theory offers the possibility of unifying all of the fundamental forces, including gravity, into a single framework. By incorporating quantum gravity into this framework, string theory could provide a complete description of the universe at both the quantum and cosmological scales. The key difference between LQG and string theory lies in their approach to the nature of spacetime. While LQG treats spacetime as a discrete structure, string theory treats spacetime as a continuous entity that can be vibrated by strings. Both approaches have their strengths and weaknesses, and it remains unclear which one, if either, will ultimately provide a correct description of quantum gravity. However, both theories are pushing the boundaries of our understanding, and it is likely that the true theory of quantum gravity will incorporate elements from both. Ultimately, the goal of quantum gravity research is to develop a theory that can explain all of the forces of nature, from the smallest subatomic particles to the largest cosmic structures. By reconciling quantum mechanics and general relativity, we hope to uncover the deepest truths about the universe, from the birth of stars and galaxies to the nature of black holes and the Big Bang. The pursuit of this knowledge is one of the most exciting frontiers in science today, and while we may not yet have all the answers, we are inching ever closer to unlocking the fundamental secrets of the cosmos. As we continue to explore the mysteries of quantum gravity, we must recognize that the journey is far from simple. It involves challenging deep-seated assumptions, embracing paradoxes, and revisiting everything we think we know about the nature of reality. The pursuit of a unified theory has become one of the most profound quests in modern physics, with implications that stretch far beyond the confines of theoretical science and into the very fabric of existence. One of the most profound areas of research in quantum gravity is the attempt to understand how the quantum effects we see at tiny scales translate to the macroscopic world we experience. The question is not just about reconciling two powerful theories. It's about explaining how gravity, the weakest of the fundamental forces, behaves on quantum scales and understanding the interplay between the tiny, unpredictable quantum world and the vast, orderly universe governed by relativity. One of the challenges that arises in quantum gravity research is the problem of the measurement problem in quantum mechanics. In quantum theory, particles exist in a superposition of states, meaning they can be in multiple positions, velocities, and configurations at once. It's only when we observe them that they collapse into a definite state. This is where the boundary between the quantum world and the macroscopic world becomes murky. How does a quantum system, governed by probabilities, translate into the deterministic world we see around us? What role does gravity play in this process? As scientists investigate quantum gravity, one theory that comes to the forefront is the concept of space-time foam. This idea posits that at the smallest scales, space-time is not a smooth, continuous surface as we typically imagine it. Instead, it is incredibly chaotic and turbulent, filled with fluctuations that arise from quantum uncertainties. These fluctuations would be so extreme that space-time itself would appear as a frothy, bubbling mass. This foam could provide insights into the nature of spacetime and the quantum structure of gravity. It also raises intriguing questions about the limits of our understanding of the universe. How can we study something that is inherently uncertain and unstable on the smallest scales? The theory of spacetime foam suggests that the very fabric of spacetime, traditionally seen as a static stage for events to unfold, is in fact dynamic and filled with quantum events. At incredibly small distances, much smaller than what can be detected with current instruments, the idea is that spacetime would exhibit quantum fluctuations, effectively spinning and bubbling in ways we cannot observe. This could imply that the smooth spacetime curvature predicted by general relativity is an approximation, and that at Planck scale distances, spacetime could be far more chaotic and unpredictable. These fluctuations are more than just theoretical. There is evidence that they could potentially have observable consequences. For instance, some scientists suggest that quantum gravity effects might have a measurable impact on the cosmic microwave background, CMB. The CMB is the faint radiation left over from the Big Bang, and its subtle variations contain critical information about the early universe. If spacetime itself were foamy, on small scales, it could leave imprints on the CMB that would be detectable with the right instruments, providing one of the first clues that we are on the right track with the theory of quantum gravity. Another area where quantum gravity could offer groundbreaking insights is in the study of black holes. We've already touched on the fact that black holes pose significant challenges to our understanding of physics, but they may also be one of the best places to test theories of quantum gravity. The event horizon of a black hole, the boundary beyond which nothing can escape, is a region where classical general relativity predicts the existence of a singularity. However, quantum mechanics suggests that quantum fluctuations at small scales should prevent the formation of such a singularity. This creates a profound conflict. How do we reconcile the smooth event horizon predicted by general relativity with the unpredictable quantum fluctuations that occur at microscopic scales? One possible resolution to this conflict comes from the concept of the holographic principle. This principle, which was first proposed by physicist Gerard T. Hooft and later expanded by Leonard Susskind, suggests that the information contained within a volume of space is not necessarily confined to that volume. Instead, it could be encoded on a two-dimensional boundary surrounding that volume. In the context of black holes, this idea suggests that the information about the interior of a black hole could be encoded on its event horizon. This would mean that the event horizon is not a simple barrier, but a complex, information-rich surface that encodes all the details of the black hole's interior. If this hypothesis holds true, it could provide a way to resolve the black hole information paradox and offer new insights into the quantum nature of spacetime. The holographic principle also ties into string theory, which is another potential framework for quantum gravity. In string theory, the universe is not made of point particles, but of one-dimensional strings that vibrate at different frequencies. The theory proposes that all forces in nature, including gravity, are the result of these vibrating strings. These strings can exist in extra dimensions beyond the familiar three-dimensional space, and they can interact in ways that create particles and forces. If the holographic principle is true, then the universe itself may be a hologram, information encoded on the surface of a higher dimensional space. This idea, though mind-bending, could ultimately explain the nature of gravity and its relationship to quantum mechanics. A related concept is the AD/CFT correspondence, which is a conjecture in string theory that suggests a relationship between a type of string theory defined in a higher dimensional space, anti-de Sitter space, and a conformal field theory defined in a lower dimensional space. This correspondence provides a mathematical framework for studying quantum gravity by relating it to a more familiar and well-understood quantum field theory. The AD/CFT correspondence has already led to important breakthroughs in our understanding of black holes, quantum entanglement, and the nature of spacetime, but it is still an area of active research, and much work remains to be done. While the path toward a fully unified theory of quantum gravity is still uncertain, the research in this field continues to push the boundaries of human knowledge. The implications of such a theory extend far beyond simply understanding the behavior of gravity at small scales. They could fundamentally alter our perception of space, time, and the universe itself. By reconciling the principles of quantum mechanics with the insights of general relativity, we may one day be able to answer some of the most profound questions about the cosmos, such as the true nature of black holes, the behavior of the universe in its earliest moments, and the ultimate fate of the cosmos itself. As we look toward the future, the search for a theory of quantum gravity will no doubt continue to inspire and challenge scientists for generations to come. And while the answers may remain elusive for now, one thing is certain: the pursuit of this theory is one of the most exciting and important scientific endeavors of our time. The universe, it seems, has far more to teach us than we ever imagined. As we continue on this fascinating journey through quantum gravity, it's important to consider the technological and conceptual challenges that stand in the way of achieving a unified theory. The difficulties are not only theoretical but also experimental. The realms where quantum gravity would manifest, extremely small scales, high energies, and intense gravitational fields, are far beyond the reach of current instruments. However, the path forward is not without hope. Scientists have been developing new ways to probe these mysteries, and while we may be far from directly observing quantum gravity effects, there are still a few exciting approaches that could bring us closer to understanding the true nature of spacetime. One such approach involves the study of gravitational waves. These ripples in spacetime, first directly detected in 2015 by the LIGO Observatory, have opened an entirely new way of observing the universe. Gravitational waves are disturbances in the curvature of spacetime caused by accelerating masses, such as the collision of black holes or neutron stars. These waves propagate at the speed of light, carrying information about the events that created them. While gravitational waves were initially predicted by Einstein's general theory of relativity, their detection opened up the possibility of using them as a probe into the most extreme environments in the universe. At the quantum scale, gravitational waves might reveal subtle features of spacetime that were previously inaccessible. Some theorists have suggested that, just as light behaves both as a particle and a wave in quantum mechanics, spacetime itself might have a discrete structure at very small scales. If this is the case, we might be able to detect tiny fluctuations in gravitational waves, revealing the quantum nature of gravity. The detection of such fluctuations would provide direct evidence of quantum gravity and offer a way to test the predictions of various quantum gravity theories, such as loop quantum gravity or string theory. While gravitational waves offer incredible potential for studying quantum gravity, another approach involves studying the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. The CMB contains a wealth of information about the early universe, including the conditions that existed shortly after the Big Bang. In particular, the CMB holds clues about the nature of spacetime itself in the first moments of the universe's existence, a period known as the Planck epoch. During this period, the universe was incredibly hot and dense, and quantum effects were likely in full force. If quantum gravity is to play a significant role in the early universe, it should leave its mark on the CMB. Researchers are looking for subtle signatures in the CMB that might reveal the quantum nature of gravity during this period. Another avenue for investigating quantum gravity comes from the study of black holes, particularly through the study of Hawking radiation. In the 1970s, physicist Stephen Hawking proposed that black holes are not entirely black but instead emit radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, is thought to arise from quantum fluctuations in the vacuum of space-time. Hawking's theory suggests that black holes slowly lose mass and eventually evaporate completely, a process that has profound implications for our understanding of gravity and quantum mechanics. However, Hawking radiation remains theoretical, and detecting it remains a challenge. If detected, it could offer a way to observe quantum gravity effects in action, providing key insights into the behavior of spacetime under extreme conditions. As we move forward, one of the most exciting developments in the quest for quantum gravity may come from the intersection of quantum mechanics and the study of cosmology. The early universe, just after the Big Bang, provides a unique laboratory for testing ideas about quantum gravity. The extreme conditions that existed in the first moments of the universe, where spacetime was highly curved and the laws of quantum mechanics were in full effect, offer the possibility of directly studying quantum gravity phenomena. The formation of the first stars and galaxies, the emergence of dark matter and dark energy, and the acceleration of cosmic expansion all involve processes where quantum gravity may play a significant role. As observational technologies continue to improve, especially in the study of cosmic inflation, we may begin to detect signals that reveal the quantum nature of the universe's birth. A particularly fascinating feature of quantum gravity research is the search for a deeper understanding of the nature of spacetime itself. In general relativity, spacetime is often depicted as a smooth, continuous fabric that can be warped and curved by the presence of mass and energy. This curvature is what we perceive as gravity. However, in the quantum realm, spacetime may not be continuous at all. Instead, it could be composed of discrete building blocks, like pixels in a digital image. This idea leads to the concept of quantum foam, where spacetime behaves more like a turbulent ocean at the smallest scales, constantly fluctuating and evolving in ways that are not easily described by classical physics. The nature of this quantum foam, and how it interacts with the forces of nature, remains one of the key open questions in the study of quantum gravity. If spacetime is indeed quantized, It could mean that space and time themselves are not fundamental entities but rather emergent properties arising from a deeper, underlying structure. Some theorists speculate that this deeper structure could be tied to the fundamental building blocks of the universe, such as strings in string theory or spin networks in loop quantum gravity. The discovery of this deeper structure would revolutionize our understanding of the universe, challenging our perceptions of space, time, and reality itself. It's also important to note the potential implications of quantum gravity for our understanding of the very fabric of the cosmos. If quantum gravity provides a way to unify quantum mechanics and general relativity, it could lead to a deeper understanding of the fundamental forces that govern the universe. Currently, we have four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. While the electromagnetic, strong, and weak forces have been successfully unified through quantum field theories, gravity remains stubbornly separate. A quantum theory of gravity could provide the final piece of the puzzle, offering insights into how all four forces are related and perhaps even revealing a deeper, more unified theory that underpins the entire universe. Furthermore, the implications of quantum gravity could extend beyond the realms of theoretical physics and into more philosophical and metaphysical considerations. If we discover that space-time itself is quantized, or that the universe behaves as a hologram, it could challenge our very understanding of reality. The nature of existence, causality, and time could be fundamentally altered by these discoveries. The universe, as we know it, might be far stranger and more complex than we ever imagined. Despite the enormous challenges, the pursuit of a unified theory of quantum gravity continues to be one of the most exciting frontiers in science. As new technologies and ideas emerge, we are inching closer to understanding how the universe works at its most fundamental level. And while the road ahead may be long and filled with uncertainty, the journey itself holds the promise of revealing the deepest mysteries of space, time, and existence. The search for quantum gravity is not just a quest to understand the laws of physics. It's a journey to explore the very nature of reality itself, to uncover the deepest truths about the cosmos and our place within it. As we continue to probe the unknown, we are bound to uncover surprises that will challenge our most cherished assumptions and open up new possibilities for understanding the universe. Whether we are studying black holes, gravitational waves, or the mysteries of the Big Bang, quantum gravity will remain at the forefront of our scientific exploration, pushing the boundaries of human knowledge and imagination. As we venture further into the subject of quantum gravity, one of the most profound questions we encounter is whether space-time itself is fundamentally discrete or continuous. Traditional physics, particularly general relativity, describes space-time as a smooth, continuous fabric that is warped by the presence of mass and energy. This smooth model has been extraordinarily successful in explaining large-scale phenomena, from planetary orbits to the dynamics of galaxies and even the expansion of the universe itself. However, when we zoom into the quantum scale, this smoothness seems to break down. Quantum mechanics, which governs the behavior of particles at microscopic scales, is inherently discrete in nature. It describes systems in terms of quantized states, meaning that certain quantities, such as energy, position, and momentum, can only take on specific, discrete values. If space-time behaves like other quantum systems, it's possible that space-time itself is quantized at the smallest scales, composed of tiny, indivisible units of space and time. This leads to the concept of quantum foam, first proposed by physicist John Wheeler in the 1950s. Quantum foam refers to the idea that at extremely small scales, space-time is not smooth and continuous, but rather fluctuates wildly, like the frothy surface of the ocean. These fluctuations would occur on scales smaller than even the Planck length, the smallest length scale in the universe, where classical ideas of space and time no longer apply. On these scales, space-time could be fundamentally grainy, with discrete units of space and time forming a kind of foam at the Planck scale. This concept suggests that space-time could be dynamic, constantly fluctuating, and evolving in ways that are difficult to comprehend within the framework of classical physics. While quantum foam is a fascinating idea, it remains purely theoretical at this stage. One of the major challenges in quantum gravity research is that the Planck length is on the order of meters, which is far smaller than anything we can currently measure with existing technology. Our most powerful particle accelerators, such as the Large Hadron Collider, LHC, are capable of probing much higher energy scales but fall far short of being able to directly explore the Planck scale. As a result, much of what we know about quantum gravity remains speculative, grounded in mathematical models and theoretical predictions rather than experimental evidence. Yet, this doesn't mean that we are entirely in the dark. One of the key ways scientists are attempting to probe the quantum nature of spacetime is by studying phenomena that occur in extreme gravitational environments, such as black holes and the early universe. These regions provide natural laboratories for testing the predictions of quantum gravity, as they involve such intense gravitational fields and densities that classical physics breaks down. Black holes, in particular, have become a central focus in the study of quantum gravity. These objects, formed when massive stars collapse under their own gravity, possess incredibly strong gravitational fields, which warp spacetime to the point where not even light can escape. The event horizon, the boundary beyond which nothing can escape, is thought to represent a point of no return, beyond which the laws of physics as we know them cease to be applicable. However, quantum mechanics demands that even in these extreme environments, there should be some level of unpredictability and uncertainty. Stephen Hawking's groundbreaking work on black holes in the 1970s introduced the idea of Hawking radiation, which predicts that black holes should slowly emit radiation due to quantum effects near their event horizons. This radiation arises from virtual particle-antiparticle pairs that spontaneously pop in and out of existence in the vacuum of space. Normally, these pairs annihilate each other almost immediately, but near the event horizon of a black hole, one particle can be pulled into the black hole, while the other escapes, resulting in the emission of radiation. Over time, this process causes the black hole to lose mass and eventually evaporate completely. The discovery of Hawking radiation, if confirmed, would provide direct evidence of the quantum nature of black holes and, by extension, the quantum nature of spacetime itself. However, detecting Hawking radiation has proven to be an immense challenge. The radiation is expected to be incredibly weak, particularly for larger black holes, and its detection would require extremely sensitive instruments that are not yet available. Nonetheless, the theory remains a cornerstone of quantum gravity research, and scientists are continuing to search for ways to observe its effects. Beyond black holes, another key area where quantum gravity could have profound implications is in the study of the early universe. The Big Bang Theory, which describes the origin and evolution of the universe, predicts that the universe began from a singularity, a point of infinite density and temperature, roughly 13.8 billion years ago. At this moment, both the effects of quantum mechanics and general relativity were significant, but these two theories are fundamentally incompatible at the singularity. This creates a deep puzzle. How can we reconcile the quantum nature of particles with the massive curvature of spacetime near a singularity? One possible solution to this conundrum is the concept of cosmic inflation, a period of extremely rapid expansion that occurred just after the Big Bang. During inflation, the universe expanded faster than the speed of light, stretching out the tiny quantum fluctuations that existed in the early universe. These fluctuations would eventually give rise to the large-scale structures of the universe, such as galaxies and clusters of galaxies, that we observe today. While inflationary models have had great success in explaining the distribution of cosmic structures, they still leave open the question of what happened at the Planck scale, where quantum gravity would be dominant. To address this, scientists have turned to ideas like loop quantum gravity and string theory, both of which attempt to describe the universe at the smallest scales. Loop quantum gravity suggests that spacetime itself is quantized, made up of tiny loops or networks of quantum fields. These loops would form the fundamental building blocks of spacetime, replacing the smooth continuum of general relativity. String theory, on the other hand, proposes that the fundamental constituents of the universe are not point particles, but rather tiny, vibrating strings of energy. These strings exist in higher dimensions, beyond the familiar 3 dimensions of space and 1 dimension of time. Both theories aim to provide a consistent description of gravity at the quantum scale, but they make very different predictions about the structure of spacetime. At present, there is no experimental evidence that can definitively confirm one of these theories over the other. Some scientists hope that advances in experimental techniques, such as the detection of gravitational waves or the study of the cosmic microwave background, could provide indirect evidence of quantum gravity. However, even if we were able to detect quantum gravity effects, it is unlikely that we would have a complete theory anytime soon. Instead, we may be left with multiple competing theories, each with its own set of predictions and implications for the nature of spacetime. What makes this quest for quantum gravity so compelling is that it touches on the deepest questions about the nature of reality. If we can successfully unify quantum mechanics and general relativity, we would gain an understanding of the fundamental forces that govern the universe and a glimpse into the true nature of spacetime itself. We might finally answer questions about the origin of the universe, the nature of black holes, and the ultimate fate of the cosmos. And perhaps, in the process, we will uncover new aspects of reality that we have yet to imagine. But, as with any scientific endeavor, the road ahead is filled with uncertainty. The challenges of studying quantum gravity are immense, and the experimental hurdles are daunting. Yet, as we continue to push the boundaries of knowledge, we are bound to make new discoveries that will reshape our understanding of the universe in ways we cannot yet predict. As the pursuit of quantum gravity continues, it's important to recognize that the consequences of successfully unifying quantum mechanics and general relativity would be far-reaching and transformative. Our understanding of the universe and the very nature of reality would undergo a profound shift. This unified theory could offer not only a deeper understanding of black holes, the Big Bang, and quantum fluctuations, but it could also have implications for other areas of physics, including particle physics, cosmology, and even the nature of time and space themselves. One of the most profound questions that arises from the quest to reconcile quantum mechanics with general relativity is the nature of singularities. Singularities, such as those found at the centers of black holes and the initial state of the universe, are regions where the laws of physics, as we know them, break down. In general relativity, a singularity is a point where the curvature of spacetime becomes infinite, and thus, quantities such as density and temperature become infinite as well. But quantum mechanics, which operates at the smallest scales, suggests that such infinities should not exist. The resolution of singularities is one of the key problems that a quantum theory of gravity must address. If we take quantum mechanics seriously, we would expect that the infinite densities and temperatures associated with singularities are an artifact of an incomplete theory. A complete theory of quantum gravity would need to replace these infinities with finite, well-defined quantities, potentially altering our understanding of what happens at the center of black holes or at the birth of the universe. Some theories, such as loop quantum gravity, propose that the singularities at the centers of black holes might be replaced with a quantum bounce that prevents the infinite densities predicted by general relativity. In these models, the collapse of matter inside a black hole would reach a point where quantum gravitational effects become dominant, and the matter would be compressed to a finite density instead of an infinite one. This would suggest that the concept of a singularity, at least in the traditional sense, might not be physically realized. Additionally, the study of black holes continues to provide crucial insights into the nature of quantum gravity. One of the most important breakthroughs in our understanding of black holes came in 1974, when Stephen Hawking proposed the existence of Hawking radiation. As we discussed earlier, Hawking radiation arises from the quantum fluctuations near the event horizon of a black hole, where virtual particle-antiparticle pairs are constantly created and annihilated. Under normal circumstances, these particles would cancel each other out, but near the event horizon, one particle can fall into the black hole while the other escapes. The escaping particle, which has positive energy, effectively carries away energy from the black hole, causing it to lose mass over time. This process of radiation emission leads to the gradual evaporation of black holes, which eventually would lead to their complete disappearance. The evaporation of black holes presents an intriguing paradox known as the black hole information paradox. According to quantum mechanics, information about a system should never be lost. It should always be recoverable, even if the system undergoes a transformation. However, the idea that a black hole can completely evaporate and leave behind no trace of the information it contains seems to contradict this principle. Over the years, many physicists have proposed potential solutions to this paradox, ranging from the idea that the information is encoded in the Hawking radiation itself to the possibility that it is preserved in a holographic form on the event horizon of the black hole. Resolving the information paradox remains one of the central challenges in the study of quantum gravity. As we turn our attention to the larger-scale implications of quantum gravity, one of the most exciting areas of research is in the study of the early universe. The Big Bang theory tells us that the universe began from an incredibly hot and dense state, a singularity-like condition where both quantum mechanics and general relativity must be applied simultaneously. However, the classical picture of the Big Bang fails to account for the quantum nature of the universe at that moment. A theory of quantum gravity could offer a more complete description of the birth of the universe, potentially resolving many of the mysteries that remain. For instance, quantum gravity might help us understand the true origin of cosmic inflation, the rapid expansion of the universe that occurred within the first fractions of a second after the Big Bang. While inflationary theory has had great success in explaining the large-scale structure of the universe, it does not fully address what caused inflation to begin or what happened at the Planck time, the earliest moments of the universe. A complete theory of quantum gravity could provide insights into these questions, offering a more unified and coherent picture of the early universe and the events that led to the formation of the cosmos as we know it. Additionally, quantum gravity might provide a resolution to the puzzle of dark matter and dark energy. These mysterious components of the universe make up most of its mass and energy content but have so far eluded direct detection. Some theories of quantum gravity suggest that dark matter could arise from quantum gravitational effects, such as the behavior of particles at extremely small scales. Similarly, the accelerated expansion of the universe, driven by dark energy, could be linked to the quantum properties of spacetime itself. These ideas are still speculative, but they highlight the potential for quantum gravity to illuminate some of the most pressing mysteries in modern cosmology. One of the most fascinating aspects of the search for quantum gravity is the way in which it bridges two of the most fundamental aspects of physics: the very small and the very large. Quantum mechanics, which governs the behavior of subatomic particles, is the theory of the microscopic world, while general relativity, which describes the behavior of massive objects and the structure of spacetime, is the theory of the macroscopic world. At present, these two theories are incompatible, and no single framework exists that can describe both realms simultaneously. The goal of quantum gravity is to provide such a framework, one that can seamlessly unify the smallest and largest scales of the universe. In addition to the scientific challenges, the search for a theory of quantum gravity raises profound philosophical questions. What does it mean to understand the universe at its most fundamental level? How do we reconcile the deterministic laws of general relativity with the probabilistic nature of quantum mechanics? Can we ever truly understand the nature of time and space? Or are these concepts simply human constructs that we use to make sense of our experiences? The answers to these questions may be far beyond our current understanding, but the quest for quantum gravity is an essential step in our ongoing effort to explore the deepest mysteries of the universe. Whether or not we succeed in unifying quantum mechanics and general relativity, the search for quantum gravity has already led to many groundbreaking discoveries and insights that have reshaped our view of the cosmos. As we continue to probe the deepest reaches of space and time, one thing is certain: the mysteries of quantum gravity will continue to inspire awe and wonder, driving scientists to push the boundaries of knowledge and explore new frontiers in our understanding of the universe. Whether we are contemplating the nature of black holes, the origins of the universe, or the very fabric of space-time itself, quantum gravity remains one of the most profound and exciting frontiers in modern physics. As we delve deeper into the implications of quantum gravity, it's important to appreciate the scale of the potential discoveries that await us. If we can successfully reconcile the seemingly incompatible forces of quantum mechanics and general relativity, it could lead to a new era in physics, one in which our understanding of the universe is radically transformed. One area where quantum gravity could make an enormous impact is in our ability to understand the fundamental nature of spacetime itself. General relativity, as we know it, describes spacetime as a smooth, continuous fabric that can be warped and curved by the presence of mass and energy. In contrast, quantum mechanics suggests that the very fabric of spacetime might not be continuous at all, but instead might be granular or discrete at the smallest scales. This idea, known as the quantization of spacetime, proposes that spacetime itself could be composed of tiny, indivisible units, much like how matter is composed of atoms. If true, this concept would have profound implications for the way we think about the structure of the universe at its most fundamental level. The question of whether spacetime is quantized is one of the central puzzles in quantum gravity research. If spacetime is indeed discrete, then the smooth curves of general relativity would only be an approximation, valid only at larger scales where the quantum effects become negligible. At the Planck scale, where both quantum and gravitational effects are expected to be significant, spacetime might exhibit a pixelated structure, with the smooth fabric of spacetime giving way to a more granular, foamy nature. This idea is explored in some approaches to quantum gravity, such as loop quantum gravity and string theory. In loop quantum gravity, for example, spacetime is described as a network of discrete loops, or spin networks, that form the fabric of the universe. These loops are thought to represent the smallest possible units of spacetime, and their interactions give rise to the larger scale phenomena that we observe. According to this theory, the continuous spacetime of general relativity is an emergent property of these discrete building blocks, much like the smooth surface of a lake emerges from the interaction of countless individual water molecules. This concept of a quantum foam has important implications for our understanding of black holes and the behavior of matter at extreme densities. In particular, it suggests that the classical picture of a singularity, an infinitely small and dense point at the center of a black hole, might not be accurate. Instead, quantum gravity predicts that the singularity could be replaced by a finite, discrete structure that resolves the infinite densities predicted by general relativity. This resolution of singularities could provide a more complete and accurate description of black holes, helping to answer questions about their interior structure, their behavior, and their ultimate fate. The idea of a granular, quantized spacetime also has implications for our understanding of the Big Bang. The classical picture of the Big Bang suggests that the universe began as a singularity, a point of infinite density and temperature. But quantum gravity implies that this singularity might not have existed in the way we traditionally think. Instead, the very fabric of spacetime might have undergone a quantum bounce, where the universe was born not from an infinitely dense point, but from a more structured, discrete state. This quantum bounce could provide a new perspective on the origin of the universe, resolving some of the ambiguities and paradoxes associated with the Big Bang. Moreover, the study of quantum gravity could shed light on the mysteries of dark matter and dark energy, two of the most elusive and enigmatic components of the universe. These phenomena, which make up roughly 95% of the total mass and energy content of the cosmos, remain largely invisible and undetectable, yet their influence is felt throughout the universe. Dark matter, for instance, is thought to account for the unexplained gravitational effects observed in galaxies, while dark energy is believed to be responsible for the accelerated expansion of the universe. Some quantum gravity theories propose that these mysterious components might not be separate entities at all, but rather manifestations of deeper quantum gravitational effects. For example, it has been suggested that dark matter could arise from the interactions of quantum fields at extremely small scales, or that it might be linked to the behavior of spacetime itself. Similarly, dark energy might be related to the quantum fluctuations of spacetime on cosmological scales. If these ideas are correct, it would mean that quantum gravity could not only provide a deeper understanding of spacetime and gravity, but also offer a potential explanation for some of the most perplexing phenomena in cosmology. Another fascinating aspect of quantum gravity is its potential to explain the nature of time. Time, as we experience it, seems to flow in a linear fashion, with the past giving rise to the present, and the present leading into the future. However, both general relativity and quantum mechanics suggest that our intuitive understanding of time might be incomplete. In general relativity, time is treated as a dimension that is woven together with space to form the fabric of spacetime. In this view, time is relative, and its passage can be altered by the presence of massive objects or the curvature of spacetime. On the other hand, quantum mechanics suggests that time might not be as fundamental as we think, and that its nature could be different at the smallest scales. In some quantum gravity models, time itself may emerge from more fundamental processes. For example, in some versions of loop quantum gravity, time might not be a fundamental quantity at all, but rather a derived property that arises from the interactions of quantum gravitational fields. In these models, time may not flow in the smooth, continuous way that we experience it, but might instead exhibit a more discrete or chunked nature, with individual time steps corresponding to the smallest possible units of spacetime. Such a radical shift in our understanding of time could have profound implications for our understanding of the universe. If time is not a fundamental aspect of reality, but rather an emergent property, it would challenge our most basic assumptions about the nature of existence. It could also have practical consequences for the study of black holes, the early universe, and other phenomena where time plays a crucial role. For instance, it could help resolve paradoxes related to time travel or the nature of causality, offering new insights into the structure of the cosmos. Ultimately, the quest for quantum gravity is not just about developing a unified theory of physics. It's about exploring the very nature of reality itself. By attempting to merge the smallest and largest scales of the universe, we are pushing the boundaries of our knowledge and expanding our understanding of what is possible. Whether we succeed in achieving a theory of quantum gravity or not, the journey itself is reshaping our view of the universe, offering new insights, and revealing the deep interconnectedness of the laws of nature. The search for quantum gravity is one of the most profound and exciting challenges in modern physics. It is a quest that has the potential to change everything we know about the cosmos, from the smallest particles to the largest galaxies, from the birth of the universe to its ultimate fate. As scientists continue to explore the mysteries of quantum gravity, we may find that the answers to the deepest questions about the nature of space, time, and the universe are more extraordinary than we could ever have imagined. As the search for quantum gravity continues to evolve, it's worth considering the various avenues that scientists are exploring in their attempts to reconcile the two theories. One of the most prominent and well-known approaches to quantum gravity is string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles but rather tiny, vibrating strings. These strings can exist in multiple dimensions beyond the familiar three-dimensional space and one-dimensional time that we experience. String theory has the remarkable potential to unify all of the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single framework. However, this ambitious goal faces significant challenges. One of the primary obstacles is that string theory predicts the existence of extra spatial dimensions beyond the familiar three that we can perceive. These extra dimensions would be extremely small, curled up in such a way that they are effectively invisible at the scale of everyday life. This idea is known as compactification. These extra dimensions are a central feature of string theory and could hold the key to understanding quantum gravity. One of the exciting aspects of string theory is its ability to incorporate gravity in a quantum framework. In the context of string theory, gravity is mediated by a hypothetical particle called the graviton, which is the quantum counterpart of the classical force of gravity. In this framework, the interaction between gravitons is responsible for the gravitational force. Importantly, string theory's approach to gravity is naturally quantum in nature, which makes it a promising candidate for a theory of quantum gravity. However, string theory is not without its challenges. Despite its elegance and potential, string theory has yet to make definitive predictions that can be tested experimentally. The need for extra dimensions, the nature of the vibrational modes of the strings, and the mathematical complexities involved makes string theory extremely difficult to test with current technology. In addition, string theory has been criticized for its lack of empirical evidence, which has led some physicists to question whether it can ever be proven true. Despite these challenges, string theory remains a leading candidate for a theory of quantum gravity because of its inherent beauty and its ability to offer a potential framework for understanding the universe at both the smallest and largest scales. String theory is still very much a work in progress, with physicists continuing to refine and expand upon its ideas in the hopes of discovering new insights about the nature of reality. In addition to string theory, another important approach to quantum gravity is loop quantum gravity, LQG. Unlike string theory, which posits that the fundamental entities of the universe are one-dimensional strings, loop quantum gravity takes a different approach by focusing on the structure of spacetime itself. In loop quantum gravity, spacetime is thought to be composed of discrete loops or networks of quantum fields, rather than being smooth and continuous. One of the key ideas in loop quantum gravity is that spacetime is quantized at the Planck scale, meaning that the fabric of spacetime is made up of tiny, indivisible units, much like how matter is made up of atoms. These loops are thought to form a network, with each loop corresponding to a tiny piece of the quantum structure of spacetime. When these loops interact, they give rise to the familiar spacetime that we experience on larger scales. This discrete structure of spacetime could potentially resolve some of the paradoxes and singularities associated with black holes and the Big Bang. A significant feature of loop quantum gravity is its focus on the nature of time and the potential for a quantum bounce, rather than a singularity at the center of black holes or at the beginning of the universe. In this framework, the universe could have undergone a quantum bounce, where the collapsing universe before the Big Bang was replaced by a new expansion, offering a different perspective on the birth of the cosmos. While loop quantum gravity offers a promising alternative to string theory, it is not without its own set of challenges. One of the difficulties of loop quantum gravity is that it does not provide a clear mechanism for including the other fundamental forces, such as electromagnetism and the strong and weak nuclear forces. Without a unified framework that includes all of the fundamental interactions, loop quantum gravity remains incomplete. Nonetheless, it has made significant strides in providing a deeper understanding of the structure of spacetime and the nature of quantum gravity. Both string theory and loop quantum gravity represent cutting-edge attempts to merge the two pillars of modern physics, quantum mechanics and general relativity, into a single, coherent theory. Each has its strengths and weaknesses, and each offers a unique perspective on the universe. The search for a unified theory of quantum gravity is still very much an ongoing effort, and it is possible that future breakthroughs will combine elements of both approaches or lead to entirely new ideas. In addition to string theory and loop quantum gravity, there are other approaches to quantum gravity that are still being explored. One such approach is causal dynamical triangulation, CDT, which is based on the idea that spacetime can be understood as a collection of simple building blocks, like triangles in two-dimensional space or tetrahedra in three-dimensional space. The key idea behind CDT is that these building blocks can be combined in various ways to create more complex structures that describe spacetime. By studying how these building blocks behave at the quantum level, researchers hope to uncover new insights into the nature of spacetime and gravity. Another approach is asymptotic safety, which is based on the idea that gravity can be treated as a quantum field theory that remains well-defined and predictive even at extremely high energies. In this framework, the behavior of gravity at short distances, or high energies, is controlled by a fixed point that prevents the theory from becoming chaotic or uncontrollable. This concept has the potential to provide a consistent description of quantum gravity, but it remains an area of active research. Each of these approaches brings new perspectives to the table, and it's possible that the true theory of quantum gravity will incorporate ideas from all of them. As we continue to explore the mysteries of the universe, it's clear that quantum gravity has the potential to revolutionize our understanding of the cosmos, from the smallest particles to the largest structures in the universe. In addition to the theoretical challenges, there are also significant experimental challenges in the search for quantum gravity. One of the major obstacles is that the effects of quantum gravity are expected to be most pronounced at extremely small scales, far beyond the reach of current experiments. The Planck scale, which is the scale at which both quantum mechanics and general relativity become important, is about meters, far smaller than anything we can currently probe. As a result, direct experimental evidence for quantum gravity is difficult to obtain. Nonetheless, there are some potential ways to indirectly test quantum gravity theories. One promising avenue is through the study of black holes, which are natural laboratories for quantum gravitational effects. Black holes represent a region where both quantum mechanics and general relativity must operate together, making them ideal candidates for testing the predictions of quantum gravity theories. For example, the study of Hawking radiation, a theoretical form of radiation emitted by black holes due to quantum effects near the event horizon, could provide important clues about the nature of quantum gravity. Another potential test of quantum gravity comes from the study of gravitational waves, ripples in spacetime caused by the acceleration of massive objects, such as the collision of black holes or neutron stars. Gravitational waves provide a unique way to study the effects of gravity at large scales, and researchers are exploring whether quantum gravitational effects might leave subtle imprints on these waves, allowing us to test quantum gravity theories. The detection of gravitational waves by observatories like LIGO and Virgo has already opened up a new window into the study of the universe, and future advancements could provide valuable insights into quantum gravity. Quantum gravity, despite its challenges, represents one of the most exciting frontiers in modern physics. The successful development of a theory that unites quantum mechanics and general relativity would not only resolve some of the deepest mysteries of the universe but would also pave the way for new technologies and a deeper understanding of the cosmos. By studying the connections between the very large and the very small, we may one day uncover a unified framework that describes everything from the quantum foam at the smallest scales to the vast expanses of the universe itself. The pursuit of quantum gravity is a journey that promises to reveal the most fundamental aspects of reality, offering a glimpse into the very fabric of the universe and our place within it. As we continue to explore the path toward quantum gravity, it's essential to dive deeper into the phenomena that could hold the key to understanding the unification of quantum mechanics and general relativity. While the theoretical frameworks of string theory, loop quantum gravity, and other approaches give us a sense of the mathematical models that might eventually describe the fundamental nature of spacetime, it's the cosmological observations and astrophysical phenomena that provide the real-world tests for these theories. One of the most intriguing aspects of modern physics is that some of the most profound mysteries about quantum gravity may be observable in the behavior of black holes and singularities. Black holes represent a region of spacetime where gravity is so intense that it warps space and time to extreme degrees. According to general relativity, the core of a black hole, the singularity, has an infinite density and curvature of spacetime. This is where the classical theory of general relativity breaks down, and the effects of quantum mechanics are expected to play a crucial role. In the traditional view, once something passes the event horizon of a black hole, it is lost forever, unable to communicate or interact with the outside world. But quantum mechanics suggests that this view might not be entirely correct. One of the key areas of research in quantum gravity is understanding how information is conserved in black holes. According to the black hole information paradox, information about the matter that falls into a black hole seems to be lost when the black hole evaporates, contradicting the principles of quantum mechanics, which insist that information cannot be destroyed. This paradox has prompted numerous ideas, ranging from the concept of holographic principles to more speculative ideas like the existence of a firewall at the event horizon. Holographic principles, in particular, suggest that the information about the black hole's contents could be encoded in a two-dimensional surface at the event horizon. This idea is strongly linked to the ADS/CFT correspondence in string theory, which suggests that a theory of quantum gravity in a higher dimensional space can be described by a lower dimensional quantum field theory on the boundary of that space. The ADS/CFT correspondence has led to many intriguing insights into the nature of black holes and quantum gravity, although it remains a speculative area of research. The study of Hawking radiation, the theoretical emission of radiation from black holes, is another crucial area in the search for quantum gravity. According to Stephen Hawking's groundbreaking 1974 discovery, black holes are not completely black but emit a faint radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, is a result of virtual particle pairs that spontaneously form near the event horizon. One particle in the pair falls into the black hole, while the other escapes, giving rise to the radiation. Hawking radiation is significant because it suggests that black holes might eventually lose mass and energy over time, potentially evaporating completely. Hawking's work raised profound questions about the ultimate fate of information that falls into a black hole. Does it escape in the radiation? Or is it lost forever, in violation of the principles of quantum mechanics? The discovery of Hawking radiation has spurred extensive research into the fundamental nature of black holes and the interplay between quantum mechanics and gravity. One important avenue of research is the study of quantum entanglement in black holes. Entanglement is a quantum phenomenon where particles that are far apart can influence each other's states instantaneously. In the context of black holes, it is thought that the entanglement of particles at the event horizon could be involved in the preservation of information. This idea has given rise to the concept of quantum gravity as a theory of spacetime itself, with entanglement acting as a crucial mechanism that could allow for the preservation of information in the universe. At the same time, gravitational wave astronomy has emerged as a powerful tool for probing the cosmos and testing ideas about quantum gravity. Gravitational waves, which are ripples in the fabric of spacetime caused by the acceleration of massive objects like merging black holes or neutron stars, were first detected by the LIGO collaboration in 2015. Since then, the study of gravitational waves has become an exciting frontier for testing our understanding of both general relativity and quantum gravity. Gravitational waves offer a unique opportunity to observe the dynamics of extreme astrophysical environments, where quantum gravitational effects might manifest. For instance, the collision of black holes produces gravitational waves that can tell us about the properties of the black holes involved, such as their mass, spin, and the nature of the singularities at their cores. While gravitational waves provide valuable data, it is still a challenge to extract information that could provide direct evidence for quantum gravitational phenomena. Nonetheless, the detection of gravitational waves is a major breakthrough in astrophysics, and it may provide us with a wealth of data that will be crucial for the development of a quantum theory of gravity. One of the more speculative and fascinating ideas about quantum gravity is the possibility that our universe is holographic in nature. According to the holographic principle, proposed by physicist Juan Meldacena in the late 1990s, the three-dimensional universe that we observe may be an illusion, with all of the information that makes up our universe encoded on a two-dimensional surface, much like a hologram. This idea is related to the aforementioned ADS/CFT correspondence and has profound implications for our understanding of space, time, and gravity. The holographic principle suggests that gravity, as we understand it, may be a manifestation of quantum effects in a lower-dimensional reality. In this view, space-time is not the fundamental layer of reality, but rather a secondary feature that emerges from a deeper quantum structure. If this hypothesis proves to be true, it could radically alter our understanding of the universe and our place within it. Moreover, a radical idea within quantum gravity is that the quantum structure of spacetime itself may not be continuous, but rather discrete at the smallest scales. In other words, spacetime might be made up of fundamental chunks, or pixels, that are indivisible. This approach is reflected in the concept of quantum foam, a term coined by physicist John Wheeler. Quantum foam refers to the idea that, at the Planck scale, spacetime is highly turbulent and fluctuating, with tiny, short-lived quantum fluctuations that cannot be described by classical geometry. This suggests that spacetime may be fundamentally granular, with a pixelated structure that could have profound implications for the nature of black holes and singularities. A theory of quantum gravity might ultimately explain how spacetime behaves at these smallest scales and provide a more complete understanding of the forces that shape our universe. At the heart of these attempts is the quest for a unified theory that can reconcile quantum mechanics, which governs the smallest scales of particles, with general relativity, which governs the largest scales of galaxies and the entire universe. As the search for a quantum theory of gravity continues, scientists are also considering the implications for cosmology. One of the most exciting prospects is that quantum gravity might provide a more complete picture of the Big Bang. According to general relativity, the universe began as a singularity, a point of infinite density and curvature. However, this singularity presents a major problem because the laws of physics, as we know them, break down at that point. A theory of quantum gravity could provide a more complete picture of the early universe, perhaps replacing the singularity with a more complex, but well-defined, quantum state. Additionally, quantum gravity may offer insights into the nature of dark matter and dark energy, the mysterious substances that make up most of the universe's mass and energy. These phenomena are not fully understood, and a theory of quantum gravity might provide new ways of thinking about them, potentially helping us uncover their true nature. In the realm of cosmology, quantum gravity could also shed light on the multiverse hypothesis, which suggests that our universe may be just one of many universes, each with its own set of physical laws. The idea of a multiverse is highly speculative, but a unified theory of quantum gravity could provide the mathematical framework needed to explore this possibility. All of these questions, the nature of black holes, the fate of information, the structure of spacetime, and the origins of the universe, are at the heart of the quantum gravity debate. While many of the ideas are still speculative, the pursuit of a unified theory is one of the most profound and exciting endeavors in modern science. Quantum gravity is not just an intellectual exercise, it holds the potential to radically change the way we understand the universe. By exploring the connections between the largest and smallest scales of reality, we may unlock the deepest mysteries of the cosmos, from the structure of space and time to the very nature of existence itself. The search for quantum gravity represents a journey into the unknown, where the boundaries of human knowledge are stretched to their limits, and new revelations about the fabric of reality are waiting to be discovered. As we continue our journey through the search for a unified theory of quantum gravity, it becomes evident that each breakthrough, each discovery, brings us one step closer to understanding the true nature of the cosmos. But despite all the progress, the path is far from clear. The complexity of the task we face in merging quantum mechanics and general relativity is unprecedented in the history of science. We are attempting to bridge two of the most successful theories in physics, one that governs the minuscule world of particles and another that governs the grand scale of galaxies and spacetime itself. To do so, we must tackle some of the deepest questions in physics. One of the most exciting ideas that has emerged from the search for quantum gravity is the idea of spacetime itself being emergent. This view challenges the traditional notion that space and time are fundamental and unchanging entities. Instead, proponents of the emergent spacetime hypothesis suggest that spacetime could arise from more fundamental quantum processes at the smallest scales. This emergent perspective is central to the idea of quantum entanglement and quantum field theory. In quantum field theory, particles are viewed not as individual entities but as excitations of underlying quantum fields that fill space. Similarly, some theorists believe that spacetime itself could be an emergent property arising from quantum entanglement and other quantum phenomena at the microscopic level. If this is true, then the smooth spacetime that we observe at macroscopic scales might be a macroscopic approximation of a much more complex quantum reality. In this context, loop quantum gravity provides an alternative framework for understanding spacetime. Rather than treating spacetime as a continuous fabric, loop quantum gravity proposes that spacetime is made up of discrete, quantized units. These units are called loops, and they form a kind of quantum foam that underlies all of space and time. In this theory, the fabric of spacetime is not smooth and continuous, but rather granular at the Planck scale, where quantum gravitational effects dominate. This discrete approach to spacetime leads to some fascinating predictions. For instance, loop quantum gravity predicts that the Big Bang was not a singularity but rather a bounce, a transition from one quantum state to another. This idea suggests that the universe may have gone through cycles of expansion and contraction, with each cycle beginning with a bounce, rather than a singularity. This theory provides a way to avoid the infinite density and curvature associated with the classical Big Bang model, offering a more robust and mathematically consistent picture of the universe's origins. The notion that spacetime is quantized is also related to the idea of string theory, another candidate for a unified theory of quantum gravity. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but rather one-dimensional strings that vibrate at different frequencies. These strings can exist in higher dimensional spaces, and the different vibrational modes of the strings give rise to the different particles that we observe in nature. String theory, in essence, seeks to explain everything, particles, forces, and even space-time itself, through the behavior of these fundamental strings. One of the most exciting aspects of string theory is its potential to unify all four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Currently, these forces are described by separate theories: general relativity for gravity, and the standard model of particle physics for the other three forces. However, string theory suggests that these forces might not be distinct at the deepest level of reality, but are instead manifestations of a single, unified force. This concept of unification is at the heart of grand unified theories, GUTs, which attempt to describe all of the fundamental forces within a single framework. String theory is one of the leading candidates for a GUT, and it could provide the key to understanding the quantum nature of gravity. However, string theory is still highly theoretical, and there is much work to be done before it can be fully validated or tested experimentally. Beyond string theory and loop quantum gravity, there are several other approaches to quantum gravity, each with its own strengths and weaknesses. For example, causal dynamical triangulation, CDT, is another method that seeks to understand quantum gravity by discretizing spacetime. In CDT, spacetime is divided into small, simple geometric elements that are used to approximate the structure of spacetime. The goal of this approach is to reconstruct the continuous spacetime of general relativity from these discrete elements, providing a way to connect quantum mechanics and gravity. Another approach is asymptotic safety, which is based on the idea that the behavior of gravity at extremely small scales can be described by a well-defined quantum field theory. Asymptotic safety suggests that the quantum theory of gravity might not suffer from the infinities that plague other quantum field theories, allowing for a consistent and finite description of gravity at all scales. This approach is still in its early stages, but it holds promise for providing a consistent and renormalizable theory of quantum gravity. Despite the diversity of approaches, all of these theories share a common goal: to find a unified description of the forces that govern the universe, from the smallest particles to the largest structures. The search for quantum gravity is not just an intellectual exercise. It is a quest to understand the very fabric of reality itself. As we look to the future, there are several exciting possibilities for how quantum gravity could reshape our understanding of the cosmos. One of the most tantalizing prospects is the possibility of testing quantum gravitational effects in the laboratory. While direct experiments on quantum gravity are difficult due to the incredibly small scales involved, there are several indirect methods by which scientists are trying to observe quantum gravitational phenomena. For example, researchers are exploring the possibility of detecting gravitational waves generated by quantum effects in the early universe. These primordial gravitational waves could carry information about the quantum nature of spacetime and provide direct evidence for quantum gravitational effects. In addition, experiments on ultra-cold gases, where the effects of quantum mechanics are more pronounced, may offer insights into how gravity behaves at the quantum level. Another exciting possibility is the study of black holes and neutron stars. These extreme environments offer a natural laboratory for testing the predictions of quantum gravity. As we continue to observe and study these objects with increasingly advanced telescopes and detectors, we may uncover new insights into the nature of spacetime and gravity. For instance, the upcoming James Webb Space Telescope and LIGO's next-generation detectors could provide crucial data on black hole mergers and other astrophysical phenomena that could help test quantum gravity theories. In addition to these observational techniques, there are also efforts underway to develop quantum computers that might be able to simulate quantum gravitational effects. Quantum computers harness the principles of quantum mechanics to perform calculations that are impossible for classical computers. By simulating the behavior of spacetime at the Planck scale, quantum computers could provide new insights into the nature of quantum gravity. Ultimately, the search for a theory of quantum gravity is not just about solving a technical puzzle. It is about deepening our understanding of the universe and our place within it. The discovery of a unified theory of quantum gravity would be one of the most profound achievements in the history of science, offering a complete and consistent description of the forces that shape our reality. It would not only answer long-standing questions about black holes, the Big Bang, and the nature of space-time, but also open up new frontiers in physics, cosmology, and even philosophy. As we continue to explore the mysteries of space and time, the search for quantum gravity stands as one of the most exciting and transformative endeavors in science. The answers we seek may take decades or even centuries to uncover, but with each step forward, we come closer to unlocking the deepest secrets of the cosmos. The universe is vast, mysterious, and full of hidden truths, and through the study of quantum gravity, we are beginning to glimpse the underlying order and beauty that governs it all. The journey to understand quantum gravity is not just a scientific quest, it is also a philosophical one. It challenges the very foundations of how we think about reality, space, and time. The current models of physics are built on two pillars: quantum mechanics, which describes the world of the infinitesimally small, and general relativity, which describes the cosmos on the largest scales. These two theories, while incredibly successful in their respective domains, are fundamentally incompatible when brought together. Quantum mechanics operates in a world where particles exist in multiple states at once, where uncertainty reigns, and where measurement itself alters the outcome of experiments. The theory relies on the principles of superposition, entanglement, and wave-particle duality. It suggests that at the most basic level, particles are not just points, but rather, waves of potential that can exist in multiple places and states simultaneously. It's a world that defies our intuition, where the rules of everyday life break down, and the familiar notion of cause and effect becomes murky. On the other hand, general relativity is the theory of gravity and spacetime, formulated by Albert Einstein. It describes how massive objects like planets, stars, and black holes warp the fabric of spacetime, creating what we perceive as gravity. In Einstein's view, space and time are interwoven into a four-dimensional continuum, and gravity is not a force that acts at a distance, as Newton once suggested, but rather the curvature of spacetime caused by the presence of mass and energy. While both of these theories have been confirmed through countless experiments, they work in fundamentally different ways. Quantum mechanics operates in a probabilistic, non-deterministic world, while general relativity deals with smooth, deterministic spacetime. When trying to reconcile them, the gaps between these two descriptions of reality become painfully obvious. Quantum gravity is the search for a theory that can unify these two distinct frameworks into a single, comprehensive understanding of the universe. One of the greatest challenges lies in understanding how the force of gravity behaves at the quantum level. General relativity treats gravity as a smooth curvature of spacetime, but at the quantum level, gravity must be treated as a force mediated by particles, just like the other fundamental forces. The quantum counterpart of the graviton, the particle responsible for mediating gravity, remains elusive. Unlike the photon, which carries the electromagnetic force, or the gluons, which carry the strong nuclear force, the graviton has never been directly observed. To further complicate matters, the traditional understanding of spacetime is completely different in the quantum world. Quantum field theory tells us that space itself is not empty, it is filled with quantum fields that fluctuate and interact. The vacuum of space, which we think of as empty, is actually filled with virtual particles popping in and out of existence. These fluctuations could be the key to understanding how gravity behaves at the quantum level, but we are still far from grasping how to incorporate gravity into this framework. Another compelling aspect of quantum gravity is its connection to some of the most mysterious phenomena in the universe, like black holes and the Big Bang. These extreme environments offer unique opportunities to test our theories, but they also present immense challenges. A black hole is a region of spacetime where the gravitational pull is so strong that not even light can escape. At the center of a black hole lies a singularity, a point where the curvature of spacetime becomes infinite, and the laws of physics, as we know them, break down. If we apply the principles of quantum mechanics, however, the singularity might not be an absolute point of infinite density. quantum effects might smooth out this singularity, and what we think of as the edge of a black hole could instead be a horizon where quantum gravitational effects dominate. String theory offers one potential solution to this problem. By considering the fundamental building blocks of the universe as one-dimensional strings, rather than point particles, string theory smooths out the singularities and provides a framework where black holes can be understood without the need for infinite density. In this picture, black holes are no longer seen as having a point-like singularity, but instead, their interiors may consist of quantum strings interacting in a way that prevents infinite density from occurring. The stringy nature of the universe could ultimately lead us to a new understanding of the most extreme environments in the cosmos. The idea of the Big Bang is another area where quantum gravity could have profound implications. The classical theory of general relativity suggests that the universe began as an infinitely dense point, a singularity, from which the cosmos exploded outward in what we call the Big Bang. However, quantum mechanics suggests that at such small scales, space-time itself would undergo quantum fluctuations. These fluctuations could have smoothed out the singularity, and rather than a violent explosion from an infinitely small point, the birth of the universe could have been much more complex. Perhaps a transition from one quantum state to another, or even a bounce rather than a singularity. This brings us to the idea of quantum cosmology, which attempts to apply the principles of quantum mechanics to the entire universe. Quantum cosmology suggests that the universe did not have a singular beginning, but instead, it could be part of a larger, cyclical process, an endless series of expansions and contractions, each one emerging from the quantum fluctuations of the prior cycle. This could provide an elegant solution to the problem of the Big Bang singularity, and offer a way of thinking about the origins of the cosmos that doesn't require infinite density or time. As we continue to probe the nature of quantum gravity, we are also confronted with the nature of time itself. In general relativity, time is treated as a dimension, much like space, and it can be warped and stretched by massive objects. But in quantum mechanics, time is treated as an external, fixed parameter, a backdrop against which the quantum events occur. This raises the question, how can time be both a dynamic, flexible dimension in one theory and a fixed parameter in another? The answer may lie in a deeper understanding of the quantum nature of spacetime itself. If spacetime is quantized, as some theories suggest, then time may also be quantized at the smallest scales. This would imply that time, like space, is not continuous but rather exists in discrete steps, each one corresponding to a quantum event. In this view, the flow of time that we experience in our everyday lives might be an emergent property of a deeper, quantum reality that is fundamentally timeless. Another intriguing possibility is that time itself might not exist in the way we think of it. Some theories suggest that time, as we experience it, is an illusion, a consequence of the way our brains process the flow of events. From this perspective, the past, present, and future could all be equally real, and the experience of time might be a subjective perception rather than an objective reality. This idea challenges our most fundamental understanding of the universe and suggests that time may be as mysterious as the space it occupies. In the end, the quest to understand quantum gravity is not just about solving equations or developing new technologies. It is about reshaping our perception of reality itself. It is about fundamentally altering the way we think about space, time, and the forces that govern the universe. Each new step in this journey brings us closer to uncovering the deep structure of the cosmos, revealing a reality that is far more strange and wonderful than we could have ever imagined. As we peer into the mysteries of black holes, the Big Bang, and the very fabric of spacetime, we are on the brink of a revolution in physics, a revolution that could change our understanding of the universe forever. The pursuit of quantum gravity is not just a scientific endeavor, but a profound exploration of the nature of existence itself, one that holds the promise of unlocking the most fundamental truths of the cosmos. The final theory of quantum gravity, if and when it arrives, will not only be a scientific breakthrough, it will be a cosmic revelation, offering insights into the very nature of reality, the structure of spacetime, and perhaps even the deepest questions about life, the universe, and everything in between. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. like the video and subscribe to the channel for more such amazing videos.